Hello, everyone. Welcome to the May 2025 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. I thought that today, for this month's AMA, we would start off with some good news. A tiny piece of good news, a little miniature carving of good news in a world that has plenty of large-scale bad news going on, but you have to look for those good little things. The good news is that Puck has been adopted. He has found his forever home. Previous listeners of Mindscape AMAs will know that Puck is our stray cat. We have the permanent cats, Ariel and Caliban, who Patreon supporters are well acquainted with. Puck was someone who showed up on our back porch a year and a half ago, and we fed him and nurtured him and sheltered him as an outdoor cat, built a little cat door so he could come into the basement. But at some point we said, look, we got to get this kitty fixed. We got to get him shots, make sure he's okay. So we trapped him, took him to the vet. And as soon as he came inside, he fell in love with the idea of being an indoor cat. He was clearly luxury oriented. He loved the soft blankets and the cat towers and all that, had no interest whatsoever in going back outside, which was our original plan. Sadly, he does not get along with other cats. And we have prior residents here, Ariel and Caliban, who get priority. And so if Puck can't get along with our cats, then he can't stay with us. So we've been looking for a new home for him. The good news is that despite his original spiciness and sharp edges, it turns out that he is the most affectionate cat in the world. He just wants to be with human beings and curl up with you and purr all the time once he gets to know you. So we thought he would be a really good fit to someone who was mostly home and could just be with him and take care of him. And so we found such a person. And the good news, even better news, I should say, is that that person is a Mindscape listener. Terrence, who lives in New York City, actually was friends with someone who's another Johns Hopkins professor who I knew. And so she made the introduction, and Terrence came down to visit. We had a sit down with Puck and we talked about it, and they all got along very well. And so I was going up to a conference in New Jersey anyway, just this week, a conference in honor of the retirement of Barry Lower, previous Mindscape guest, and a bunch of other Mindscape previous guests were there at the conference. And I took Puck with me and just drove him up to New York and dropped him off at Terrence's place. And they seem to once again get along great. And I think it's going to be a wonderful, wonderful fit. And Puck is now a New York kitty cat. He's very, very adaptable. He abides with whatever situation he's in. He didn't even mind the drive up, even though he'd never been in a long car ride before. So I'm very, very happy with how things have worked out. I'm sure there'll be future updates on various kitty cats throughout. Most Mindscape talk is not about cats, but there's got to be a little bit of talk about cats because it's good news in a world where other things are going badly. With that, we can get into the AMA proper. Of course, remember that the questions for the Ask Me Anything episodes are asked by Patreon supporters. It's really easy to be a Patreon supporter. There's a barrier. There's sort of a potential barrier, physicists would say, to like signing up with Patreon and putting your numbers in or whatever, but it's easier than it looks. And once you're there, you can support creators of all sorts, including the Mindscape podcast. So just go to patreon.com/Sean M. Carroll, M for my middle initial Michael. And then you can pledge to support Mindscape, and you get ad-free versions of the podcast. You get to ask questions for the AMAs. And also for every episode, I do a little short reflection audio that I share with Patreon supporters. So it's worth doing, if only to feel like you're supporting something that provides hours of entertainment here at Mindscape in various ways. And speaking of which, let's go. Anonymous asks, are there any sci-fi tropes or prevalent physics ideas in general which you would place on an even lower credence on being possible than faster-than-light communication? I'm actually, if you know my talks, my feelings about science fiction in movies and films, TV, novels or whatever, I'm pretty forgiving. I don't have, don't take great pleasure in sitting and watching a movie and picking apart the scientific inaccuracies. What I care about is whether or not it throws you out of the movie, whether you go like, no, that's not what would happen. So I don't mind faster light communication or travel in a science fiction movie. It's clear why they're doing it. It makes the rhythm and the time scales of the story that they're telling be more similar to the rhythm and time scales of Earth-based stories. Battles on land or on the sea or whatever are more similar to space battles if you can go faster than the speed of light, because you can get places more quickly. So I don't mind that, but of course, there's always also something pleasurable to be gleaned from a good story that doesn't violate the laws of physics just to tell a more familiar story, and that's worth doing. So the things that bug me are not like, oh, that would really never happen, so much as this is just lazy and they always do it and they don't even question it, and it's not realistic. And the example that comes to mind, it doesn't bother a lot of people, but it bothers me, is just that in almost every science fiction, space opera kind of film, they say, well, we have artificial gravity on our spaceships. So life on the Millennium Falcon or Battlestar Galactica or whatever is not that different than life on Earth or on a battleship here on the oceans. You're still pulled down toward the floor. And I think, number one, there's actually not any way to do that in terms of the laws of physics. You can create the illusion of artificial gravity by spinning a ship, but they generally don't do that because they want their ships to sort of look sleek and aerodynamic, even though they're moving through space. And then there isn't really any way in the known laws of physics to artificially pull things in some arbitrary direction just to give human beings a comfortable feeling that there's a floor beneath their feet. It's not something that gets in the way of storytelling in any way. In fact, it makes the storytelling much easier. It certainly makes it more intuitive and recognizable for the viewer of the movie to see people standing up with gravity pulling them toward the ground. But it's just universal and just such an obvious cheat. It's not what would really happen in the actual science fiction. So I would respect a version of a space opera kind of story that didn't make use of that lazy trope of artificial gravity on the spaceships. It would be much more expensive and weird. Of course, there's been science fiction movies set in the solar system, for example, like Europa Report or whatever, where they don't have artificial gravity. It tries to be more grounded and realistic. Generally, roughly speaking, if your movie shows people flying through our solar system, they try to be realistic about artificial gravity. Once they're out in interstellar space, they say, forget that. That's too much effort. And not only on the ships, right, but between the ships. Like everyone has a common orientation in space. There's up and down in space or something like that. That's not what it would be like. So it's not, entirely a violation of the laws of physics, because you can imagine things. It's very, very hard to imagine things. It's much harder than most people think it is to imagine artificial gravity. But that's the one thing that sort of always rubs me the wrong way just a little bit. Now I'm going to group 3 questions together on a common theme. Rami Fischler says, do you use AI tools in your professional life? If you do, which AI tools do you use and how do you use them? For example, do you use AI to solve equations? Joseph Eli says, something I've realized in the past month or so is how monumental AI is as a learning tool in a way that it feels like a lot of people are underappreciating. Sure, AI can write code and help you troubleshoot your router, but if you're curious and know how to ask good questions, you can learn about literally anything you want at any time, perfectly tailored to your attention span and current level of understanding. This feels like it could be the biggest cognitive phase transition in human history. Am I being too sensationalist about this, or is it really that big of a deal? And then Yazan al-Hajari says, I'm fascinated by the interplay between scientific and artistic creativity. While the language of the arts now seems disrupted by AI, challenging our notions of human creativity, I'm excited by the opportunities this presents. By automating mechanical routine tasks, AI allows adaptive artists to focus on what is truly creative. How do you see this dynamic playing out in the sciences, which are inherently objective and not personal? Can you share your thoughts on how this might shape the future of scientific exploration? So I think that, I mean, maybe I could have ordered the questions differently. I think that Joseph's question in the middle there provides a pretty good answer to the other two questions, about how AI can be used. I think AI is tremendously useful when used in the right way. It's weird. I've said it many, many times, but the current large language models we have are intentionally tuned to make you think you're talking to a human agent. But you're not, and there's obvious reasons why they want you to act as if you are, but it also leads us to sort of not use it in the most ideal way. And I think that Joseph is completely correct to sort of answer Rami's question about how I use AI in my professional life. By far, the most useful application that I have of it is learning new things. And it's not it's helpful if you know enough about the subject to ask good questions about it. And then what you're doing is filling in your gaps. Like when you learn from a textbook, which I'm all in favor of, I've written textbooks and I'm writing another one, you are faced with the problem that the author of the textbook has the job of anticipating your confusions, right? What is it that you think you understand and don't quite? So they have to sort of try to say, well, you might think this, but maybe that. Whereas with the AI, you can just tell it what your confusions are. You're like, I don't understand how this leads to that or why they say this, or even things, what I found it useful for, in mathematics, for example. When people say, well, here's a certain construction mathematically, and it leads to this conclusion. And often there's sort of background knowledge going on that I don't have if it's an area of mathematics that I'm not completely familiar with. And so there are implications of this result that are not immediately obvious to me, but would be obvious to someone who is embedded in that area. And you can ask the AI. You can ask the large language model. I don't have favorites or anything like that. I use GPT sometimes. I use Claude, which is Anthropic's sometimes, whatever. But you can say like, okay, why do I care about this result? What is the implication? What is it useful for? And it will tell you. Now, of course, it's not always right. You can also ask it to just do a calculation. I don't ever ask AIs to solve equations because, that's literally exactly the kind of thing where I would want to be very sure it didn't make mistakes. And the AI will always make mistakes. Not always, I suppose, but it will frequently make mistakes. And therefore, it's more useful to use it in a situation where it's sort of working hand in hand with you, right? Where you are listening to what AI says and then judging whether it makes sense or not. The idea of just having the AI write things for you without even reading them. People write science papers, have the AI write science papers for them without even reading them. It's perfectly obvious that they do that. And that's just bizarre and crazy to me. But I can ask an AI, like I asked ChatGPT the other day, or not ChatGPT, I guess. I don't know. The labels on the different AI models completely escape me these days. But I asked, as a beam of light comes from a distant galaxy to the Earth, it will travel through dark matter in the conventional cold dark matter model in cosmology. Some of that dark matter will be in the galaxy where the light leaves. Some of it will be in our galaxy where the light arrives. But some of it will just be spread thinly throughout intergalactic space in between the voids. There's more distance that the photon travels in the voids, but there's a lower density of dark matter. So what wins? Does the photon travel mostly through, is most of the column density of dark matter from the local concentrations in galaxies and clusters, or is it mostly in the voids in between? And it set up the calculation. It says, oh, here's how to do it, and I can look up these numbers. One major leap forward that the most recent versions of GPT have is that they can cite sources. And this has always been my complaint, because when AIs just make things up, you don't know, right? And it's much more helpful to be able to look at a paper written by a human being to verify where this idea comes from. But now ChatGPT or GPT, whatever most recent model it is, will tell you, will say, okay, go to this archive paper, and this is where I got this idea from. that is enormously more helpful. So anyway, I don't necessarily believe the answer that GPT gave me, but it sets up a way to do the calculation that I can check myself if I want to, and then I can decide whether or not I need to go into more detail, whether or not I want to do it in a different way. I can even ask it, is there a different way to do it, etc. So in that sense, learning new areas, setting up calculations in certain ways, also, hugely helpful is just, has anyone thought about this before? Right? Like I'm trying to do something. Well, has anyone else already done it? I was asking it about, a model which might help to explain the Hubble tension. And I said, which we talked about with Adam Rees on the podcast quite a while ago, and with Mark Haminkowski more recently. And, it could tell me, well, this paper did this kind of thing, which is similar, but not exactly the same, right? Hugely, hugely useful because it knows a lot more stuff than I do. It's not a replacement for human being or human thought. So to Rami's question, that's how I use AI. To Joseph's question, yeah, I think it's hugely influential exactly in that way of helping people learn things. Whether it will be a true cognitive phase transition, I'm not sure, because I'm not sure how many people are really devoted to the idea of learning new things. For those of us who are, it's very, very useful. And I think, you see that a lot of people just want to use it to replace human cognition, which I think is not the best use of it. And to Yazan's question, yeah, I think that scientists will get better at using it, right? And it will, again, not replace scientists, but a scientist plus a good AI hand in hand is better than a scientist all by themselves, and that's going to be very useful for science going forward. Jamie says, the doomsday argument suggests that statistically you are likely to be born somewhere in the middle of the total human population, etc. Doesn't this and related arguments about the state you find yourself in, maybe including anthropic reasoning and self-locating uncertainty, subtly depend on some set of subjectivity or consciousness metaphysics? If we are just an epiphenomenal emergent property, then in what sense do we find ourselves to be here and now? So I'm not completely sure that I understand exactly what you're getting at with this question, because there's many things going on. I mean, there's details of anthropic reasoning. I mentioned on the podcast before, I think I did a whole podcast at one day on the philosophy of cosmology, because I teach that in one of the courses I teach in the philosophy department here. I don't think that conventional anthropic reasoning is done correctly, because I think that the first move in conventional anthropic reasoning is to imagine that we are chosen randomly from some reference class of observers in the universe. And I think that's just not really true unless you narrow down that reference class to people exactly like me, which is a very tiny class compared to the general people or general observers or whatever. So anyway, but I don't think that's the question you're mostly getting at. You're asking about subjectivity or consciousness or something like that. I don't think it depends. Well, let's put it this way. In my consciousness metaphysics, which is entirely physicalist and emergentist, I'm saying that consciousness is just a way of talking about the collective behavior of ordinary matter arranged in certain configurations, etc. So I see no problem whatsoever in asking questions like, there are many such configurations that are essentially identical to each other, scattered throughout the universe. What is the chance that I'm any one of them? What do most of them see when they look outside? Things like that. I see no problems with that at all. You're using words like consciousness and observer, but they're just stand-ins for certain pretty well-defined statements about configurations of matter. There's nothing spooky about it or anything like that. I guess if you did have a spookier metaphysics, if you thought that consciousness was something over and above a certain collective behavior of atoms arranged in a certain way, then you might be troubled by questions like, in what sense do I find myself to be here and now? Like, where else and when else could you find yourself to be? And that's why it's hard for me to answer this question. But maybe if you thought there was some ineffable essence of self that was uniquely you and was different than the other configurations of matter that were naively similar to you, then maybe you would have different questions about that. But I think that for a general physicalist who thought that consciousness is emergent, this is not really an issue. Victor Tiffany says, after you answered my question about energy conservation in the many worlds interpretation of quantum mechanics, you added, there are real worries that you can have about many worlds, but energy conservation is not a true scientific worry. So what are those real worries? I think I've said what the real worries are at different times, but not everyone listens to every word. So it's worth mentioning again. It's been a while. I think there are two sets of worries that are valid. One is the question of deriving the Born rule, the probabilities in many worlds. And it's not that I don't think we can. I think we can. I think I know how to do it. But the origin of probability in many worlds is very, very different than what it would be in a truly stochastic theory. Or in a truly stochastic theory, single world theory, you can just say, well, there's something that we don't know and can never know about what will happen next in quantum mechanics, and the best we can do is assign a probability to it, and we can figure out what that probability is by looking at the frequencies of previous events, and we get that the Born rule fits the data, and it all sort of makes sense. It's at least, not only does it make sense, but it's comfortable and familiar to us, okay? Whereas in many worlds, as has been pointed out many, many times, every allowed outcome happens. The word allowed is super important there. Some outcomes are not allowed. All outcomes that are supported by the Schrödinger equation and the current state of the quantum state of the universe are allowed, which is very, very different than saying everything happens. But anyway, many different outcomes actually do happen. And with 100% probability, they will happen in one of the branches of the wave function, right? If I have a spin that is a superposition of spin up and spin down, and I measure its spin, in one branch, it's definitely going to be spin up. In the other branch, it's definitely going to be spin down. Nothing probabilistic about it. So where do the probabilities come from? And again, I think there's an answer to this question, and it has to do with self-locating uncertainty and things like that. But the kind of answer it is deeply different than the kind of answer it is in the case of a truly stochastic theory, and therefore I think it is okay to worry that we are cheating. We know what the answer is that we want to get. We want to get the Born rule. We want to get that the probability is proportional to the wave function squared. I think we do get that in a very natural way, but a very different way than what we're used to. So we should be thinking very, very deeply about whether we're just cheating ourselves. The other thing to worry about in Everett is that it's a very austere theory. So the origin of structure, broadly construed in the quantum state of the universe, is a big question. Why do we see a world with three-dimensional space and matter and energy rather than just seeing a wave function? Okay. Again, I think it's perfectly possible to answer this question, but I think it is much less answered than the probability question, because the answer that we want is a lot more detailed and structured, as it were, than just the probability question. So there's a lot of work to be done, and this is one of the biggest things that I'm working on myself right now. How do you take that abstract quantum wave function and divide it up using words like emergence and coarse graining and effective theories and things like that, and say that, oh, look, there's a classical limit with matter and particles and things like that. The reason why this is a uniquely Everettian problem is because Everett's theory is the simplest theory of quantum mechanics. It is the one that doesn't have any extra stuff. It just has the quantum state and the Schrödinger equation. Other approaches to quantum mechanics don't need to address the structure problem because they just put the structure in as part of the posits of the theory. You have particles moving in space if you're Bohmian. You have certain ways that the wave function collapses if you're an objective collapse person, and all of these rely on this extra structure. So they quote unquote answer the question by just making an assumption that it's there, right? And maybe it is there, so that's perfectly valid. I think that it is better if we can derive it from something more fundamental, but that doesn't mean that it's not work to actually do that derivation. Henry Jacobs says, on idealism versus naturalism, there's a theme in mathematics towards doing things backwards, e.g. reconstructing a manifold from its ring of smooth functions, reconstructing the shape of a convex domain from the spectrum of the Laplace operator. By the way, that last technical thing that Henry is referring to, reconstructing the shape of a convex domain from the spectrum of the Laplace operator, that is the famous, can you hear the shape of a drum question. When you tap a drum head, the vibrations are given mathematically by the spectrum of the Laplace operator, the set of eigenvalues of this differential operator. And the question is, can you uniquely reconstruct the shape of the drum head from knowing the frequencies of those vibrations? And the answer is sometimes. It depends on some extra assumptions. Anyway, Henry continues. One takeaway message from these examples is that sometimes what you viewed previously as fundamental versus emergent or derived can be reversed. Have you ever pursued the possibility that one can view idealism and physicalism as two sides of the same coin? So I completely agree that in many cases of interest, the question of what is fundamental and what is derived is not well defined. You can go either way, right? And that standard set of examples of that are dualities in quantum field theory and quantum gravity. A duality is really when you have two different theories, let's say two different classical theories that you can quantize, and you can get exactly the same quantum mechanical theory by quantizing these two very different classical theories. So to say, well, which is the right one is an ill-posed question. They're both perfectly good classical avatars of the same underlying quantum theory. So it's not that one is fundamental and one is emergent. They're both on an equal footing. And there are other examples, like in math, as Henry said, there's sort of different ways to give the data and then derive other features from that. And the starting point is not unique. That data you start with can be chosen in different ways. Axiomatic systems are often very similar. You can start with different sets of axioms and prove exactly the same complete set of theorems. Now, applying that to idealism and physicalism, no. I don't really think that works in any useful way. Maybe it does. Yeah, you're asking me what I think. I think it doesn't, but I could be persuaded otherwise. I mean, look, to me, not to be too straightforward and naive about it, but there's just that super obvious reason why idealism is a non-starter, which is that we all of us minds here in the universe, as far as we can tell, experience the same physical reality. Right? We all think that space is three-dimensional and there are atoms and particles. I mean, some of us might not know it, but we say things about the world as long as we're not literally making mistakes that are compatible, right? The same physical world. And so there's two possibilities. One possibility is that that's because there is a physical world that is really there and we're just all experiencing it. The other possibility is, I don't know what the other possibility is. Somehow mind is fundamental and mind constructs the same physical world for all of us. That kind of hypothesis is just wildly unsatisfying compared to the physicalist hypothesis or the naturalist hypothesis. In physicalism, I can just tell you what the stuff is, and I can tell you the equations that it follows. And an idealist has to sort of shrug their shoulders and say, yeah, for some reason, all of our minds construct the same physical reality obeying these very, very specific equations. It just seems like magic and wishful thinking to me. So I don't think it is a case of getting the same stuff from different starting points. I think it's a different thing than that. Thies Janssen asks a priority question. Remember that priority questions are things that Patreon supporters get to ask once in their lifetimes. If you're reincarnated in a future body, then you get to ask two priority questions. That's a rule I just made up right now. But you have to have proof that you're truly reincarnated. You can't just assert it. So Thies says, quantum mechanical effects are often associated with extremely cold or small systems, since in systems with higher energy or many particles, decoherence typically occurs before quantum effects can have a measurable impact. As far as I know, the quantum mechanics of quasi-particles, such as electron holes, is a well-established area, even though these quasi-particles exist within systems containing many particles. More controversially, I've read that the high efficiency of photosynthesis may be due to quantum effects, specifically the idea that an electron hole can exist in a superposition, spreading wave-like through chlorophyll to the reaction center. To me, this sounds more like a principle of least action than genuine quantum superposition. How is it that quasi-particles can exhibit coherent quantum behavior within large complex systems, and does this open the door to quantum processes occurring in environments where they are not typically expected? I think it's a very good question. Sadly, the only true convincing answer to this question would involve a lot of math and a lot of calculating. I don't know why I pronounce calculating in that weird way. A lot of calculating, which I haven't done and I'm not really going to try to start doing right now. But here's the thing. You're right that there's sort of conventional wisdom that quantum effects become hard to detect in classical systems because they're big and warm and decoherence happens very rapidly. Warm is relevant because that means things are jiggling around, things are emitting infrared radiation, things are interacting with the environment, all of which lead to rapid decoherence. So if that's why quantum computers, you want to make them very, very cold so that like the random infrared photon in the room does not come along and ruin your quantum computation by entangling with your qubits. But there's a subtlety there. I know that those are the words that we usually say, but there's a huge subtlety there. And think about it in terms of the uncertainty principle. Okay, the uncertainty principle says that there's no quantum state, let's just say for a single particle to keep our lives easy, there's no quantum state for which there is minimal or no uncertainty simultaneously in position and momentum, right? So if you're well localized in position, then you are all spread out in momentum, or vice versa. So what that means, the reason I'm bringing it up is if you had a particle that was in a single state of position, an eigenstate of position, so we knew exactly what its position was, then when you think about it in terms of the momentum basis or the momentum observable or whatever you want to say, it is a superposition of many, 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 many different things. So when you ask of a certain quantum state, is it in a superposition or not? That is not a well-defined question, right? Superposition in what basis? With respect to what observable is the question that you can ask. And any quantum state will be not in a superposition with respect to some observables, and yes, in a superposition with respect to most other observables, okay? So decoherence puts quantum systems into certain states called pointer states, the ones that are sort of robust against measurement, right? Typically, position is a characteristic of pointer states, but if the things are big enough and macroscopic enough, both their position and their momentum can be defined fairly narrowly because both their position and their velocity, let's say, can be defined fairly narrowly. Just because they're big and macroscopic and there's a 1 over the mass in the denominator. So when you have these intermediate scale things like quasi-particles in a solid, or for that matter, just electrons in a conductor, right? Electrons in a conductor are not little points. Their wave functions are a little spread out because that's what they can do. Because there's nothing, the interactions with the environment localize them into some kind of quantum state, but that quantum state is not localized in position. When you ask about decoherence and the effect it has, you have to say, what is the state into which you decohere? What is the form of the quantum state that you get after decoherence has happened? It's not always just everything is localized to a point. That's very, very common because of the locality of the laws of physics and the way that the environment is set up. But in certain environments, like in a conductor or perhaps in photosynthesis reactions in a biological system, the thing that the quantum system settles into after being observed can be spread out in some very obvious way, in some very noticeable way, or very important, I suppose, is the relevant adjective, way. So that's why you have to do the calculation. That's why you have to actually think about things very carefully. So when you ask, does it open the door to quantum processes occurring in environments where they are not typically expected? Well, yes and no. There are good reasons why the typical thing that happens when systems decohere is they localize in space, right? In order for that not to be the answer, you need to set up the system that you're in a very particular way. And so that's the question about things like quantum biology. Are there contexts in biological processes where the physical setup allows the quantum state of something like an electron to be all spread out? that is conceivable, but it's not easy or obvious. You have to sort of make it work. Could it be happening in other contexts? Sure, it could be, but you would have to actually show that that's what happens. You can't just say, well, things can be spread out, therefore they are spread out all over the place. You have to actually do the work. Richard Williams says, I've heard you and David Deutsch say that you'd be surprised if the brain was making use of quantum computing. Good, as we just talked about. You both seem to think that it's probably just a classical computer. If quantum computing proves to be useful in the future, what makes you so confident that evolution hasn't hit on it already? Is there something about our biology that rules it out? Right, so I was going to group these two questions together, but I decided to just put them one after the other. Evolution isn't that clever. Evolution is clever, but there are fundamental physical constraints that evolution has to bump up against. So the reason why evolution is not expected to use quantum coherence and quantum computing all the time is exactly the same reason why it has been very difficult for we human beings to build a quantum computer. Because you have to be in a very, very specific, very, very highly specialized kind of environment in order to maintain quantum coherence of multiple qubits. Typically, those kinds of environments that we human beings engineer are super duper cold because even occasional infrared photons would prevent the calculation from being carried out. In a biological system, that's just very hard to do. It's not impossible, as we just said, but it's just very hard. So it's not surprising that evolution doesn't use quantum computing in a robust way all the time. Stevie CPW says religious institutions, charities, and universities raise enormous amounts of money and don't pay taxes. The theory is that they are exempt because they're not for profit, but they behave like businesses and have accumulated great wealth. To me, this is inappropriate and unfair to honest taxpayers. How do you feel about it? Well, I think that the system can be abused for sure, but I think that overall the system is good. When you say, so the question is, how do we treat nonprofit organizations vis-a-vis taxation? And you say they behave like businesses and have accumulated great wealth. Well, they don't completely behave like businesses. Most universities and charities and things like that are not in it for the money. That doesn't mean they don't accumulate a lot of money, as we've been having discussions about in the discourse these days. Big-time universities like Harvard or Stanford or whatever have large endowments. But they use those endowments not to give dividends to shareholders. They use them to build laboratories and provide aid for students and pay faculty salaries and a whole bunch of other things, okay? So likewise for religious institutions and charities and so forth. And, ideally, when the system is working well, they use the money they accumulate to do the good nonprofit goals that they have. Of course, this can be abused, right? And certainly certain churches, certain charities, probably certain universities, I'm not going to pretend otherwise, abuse the system in some way. But I think that the response to that is to crack down on abuses of the system, not to change the system in some fundamental way. Jameson says, what practical steps would you recommend to help the political situation in the United States? The only honest answer here, Jameson, is I don't know. I have, there's people who have put a lot more work than I have into, short-term actions you can take, organizations you can join, letters you can write. I do think that it's good to be politically engaged. I do think it's good to communicate with your representatives. I think it's good to be engaged with local politics as well as with national politics, whether that's writing letters and emails, phone calls. I'm told that phone calls are much more effective than emails, et cetera. I don't know why that is, but, okay, showing up to town halls, whatever it is. I think that showing up to demonstrations and protests, wearing T-shirts or whatever, putting a sign in your yard. There's many ways to be politically engaged, which both give you personally a feeling of at least trying to do something and also potentially have an impact if many, many people do that. Nothing like that I can think of is going to lead to dramatic short-term change, okay? But that's okay in some sense, or at least it's not okay. I would like dramatic short-term change, but that is not a reason not to do it, I suppose, is what I should say. Becoming politically involved and aware. I do think that It's becoming clear, I think, that in the United States we have done a bad job of creating a public that is politically, what can I say, responsible. In other words, in a democracy, the people are given the authority to choose their representatives, and I'm a huge believer in that. And I don't think it's because the people are the smartest way to choose the representatives. I think it's because the people have a right to choose who is governing them. They have their interests, and the best way, in principle, to have those interests protected is that they can choose the people who are doing the protection. But clearly, people are not very well informed about politics, and even more strikingly, people are not very devoted to what I consider to be the foundational ideals of American democracy. Separation of powers, building coalitions of people who might not agree on everything, compromise within the different branches of government, things like that. Just the idea of free and fair elections. A whole bunch of things are just not as valued by a lot of Americans as I would like them to be. So the longer term strategy, I think, is to build up that kind of responsible, educated, knowledgeable citizenry. Don't ask me how to do that. I don't know how to do it. Schools should be involved. The government should be involved. The media should be involved, But I think that having the goals is something important. I do think that so that's a short-term thing, a long-term thing. There's a very obvious medium-term thing, which is that, not to be alarmist about it, because I don't think this is alarmist at all, but ensuring that we have free and fair elections in 2026 and 2028 is probably the single most important thing that needs to be done. Can an individual person sitting at home make that happen? No. They might be able to contribute to making it happen. It's a frustrating thing sometimes to be a citizen of a very, very large democracy like the United States is, because you're only one person among over 300 million, right? And it doesn't seem like your voice has an instant impact. But there are accumulated long-term effects. Many people having similar opinions and pushing in similar directions over time can have an impact. Caring about the fact that election integrity is in danger is super duper important. Making it an issue, keeping it alive, taking seriously the fact that certain parties are trying very hard to not let certain people vote, to not let certain votes be counted, to put people in place who will let them overrule the results of elections. Like, all of that should be a super duper high priority thing to pay attention to and thing to make sure it doesn't happen. And I don't think that we're anywhere close to the right level of alarm and worry and concern about that as we should be, given all the evidence that we have. So I don't know, that none of that is very practical. Sorry. Now, being practical is really not my stock in trade. I'm not the person to ask about that. I'm sorry about that. Ike Pierstorff says, science communication on any given topic comes in at least two parts. A narrative part, like Schrodinger's cat, and, for lack of a better word, a substantial part, like the equations of quantum mechanics. Like all people, I know little to nothing about most things, yet I want, and in some cases, like vaccines or medicine, I need to have opinions, else I will be unable to ever decide on any action. What is a good strategy to have an informed opinion when I cannot judge the truth of the narrative by the quality of the substance? I've met people who are doing their own research and the outcomes are usually not great. Yeah, doing your own research is not great, because doing research is a skill overall, and doing research in a specific area is an extra skill. No one is good at doing research in all the different areas. And of course, when people say they're doing their own research, they don't mean they're doing their own scientific research. They mean they're picking and choosing certain things to read and making their choices based on that. It's a very, very bad way to go through life. Look, we have to balance the the fact that some people are more knowledgeable and expert in areas than we are, with the fact that no people are perfect. And we have to judge our own individual level of knowledge about things. And the more we know about something, the more legitimate it is to disbelieve what most experts in the field believe. If you're completely not an expert in something, then I think that by far the right strategy is to put the largest credence on what most experts do believe. It's easy to find examples where the opinions of most experts will be wrong, but it's not easy to come up with a strategy where you can regularly outwit the majority of experts, okay? If you could, the experts would change their minds. Obviously you should try to pick your experts well. There are lots of self-appointed experts or people who become famous because they were on Oprah Winfrey or whatever, not because they're true experts. One thing that I like to say, maybe I don't say it enough, but there is something called Google Scholar, right? All academics know about this, but you can go to Google Scholar, scholar.google.com, or the equivalent thereof. I don't know exactly what it is. It's a bookmark for me. And you can look up scientists or academics more broadly, not just scientists. You can ask what papers have they written, and you can ask who has cited those papers. And as a very rough first guess at whether someone is a respectable academic, a respectable researcher and intellectual in a certain area, are they making an impact in that area? Are they simply a popular talking head who doesn't actually do research, or are they churning out real scientific papers or, refereed publications? It's easy to tell the difference if you just go to Google Scholar and ask, and no one does that. Or not, some people might do it, but very few people do that. They seem weirdly willing to just go along with people who talk loudly on the internet, and that's weird. So if you can't do your own research, which is often the right thing not to do, at least what you can do is try to figure out whether the experts whose opinions you're listening to are respectable experts or not. And that's actually relatively easy to figure out. All right, I'm going to group these two questions together. Crather Luca says, ontologically speaking, do you view the wave function of the universe as being real, or do you view it as a description of how the universe evolves? And Bill Quirk says, do you believe the Schrodinger equation reflects an underlying physical reality, or is it just a powerful computational tool? So these are two slightly different questions because the options that we're given are slightly different, but clearly, they're in the same spirit. Bill Quirk's question is distinguishing between the Schrodinger equation, which governs the evolution of the wave function. You could substitute the wave function for where Bill says the Schrodinger equation. But the distinction is between it's reflecting physical reality or is it just a computational tool. So here is the difference between a realist approach to quantum mechanics, where it says exactly that the wave function is mapping onto some physical reality, versus an instrumentalist or epistemic version of quantum mechanics, where it's just something to predict observational outcomes. To that distinction, I think it's, to me, overwhelmingly likely that it represents physical reality. Wave functions can interfere with each other, right? That's what you see in the double slit experiment, et cetera. People always say the double slit experiment, including me, but every calculation of the probability of some particles being created at the Large Hadron Collider also involves interference between different quantum processes. When you calculate Feynman diagrams for some process, so I smash two quarks together and I look at what comes out, and I say, well, I'm going to look at cases where a Higgs boson is produced and then it decays into two photons, okay? Well, there are many, many Feynman diagrams that contribute to that process. And the thing that you do is you calculate the contribution from each Feynman diagram, and then you add them together. And sometimes they're all positive and they add up. Sometimes some are positive and negative and they cancel out. There's interference, right? So that ability of the wave function to interfere seems to me to be characteristic of physical reality, not of just a computational tool. But people disagree about that. Crather Luca's question is a slightly different distinction between two realist ontologies, but one which says the wave function is real, and the other, if I'm interpreting this correctly, and the other says the wave function is a description of what is real, but it's not the real thing itself. Again, to me, this is perfectly obvious. It's a description of what is real, but people will talk casually about this, and you're supposed to be quick enough to figure out what they're saying. So when people say, the universe is a wave function, they mean the universe is the universe. The universe is a unique universe-like thing. It's not anything else, but it is exactly mathematically isomorphic to a wave function evolving according to the Schrödinger equation. That's what they mean. It's exactly like when people say the electric field is a vector field. No one ever says to them, like, are you saying that a vector field, that's just a mathematical construction? Are you saying that the universe is made of math? No, the universe is made of an electric field. I just describe it mathematically as an element of a certain vector space, right? And the same thing exactly is supposed to be true for the wave function. The universe is the universe, but according to certain versions of quantum mechanics, its behavior is exactly described by a vector in Hilbert space. Libby Gavas says, the real question is, what is your favorite brand of dry vermouth for making a martini? This is an excellent question because, to be fair, I have not put the requisite effort into looking through the possibilities of dry vermouth. I've defaulted to Dolin, which is one of the standard brands. It's easily available everywhere. Seems to work fine, seems to help out whatever gin I'm putting into the martini. I put a lot of effort into thinking about gins and trying out different gins, and they are different. It seems clear that the vermouth should be treated equally importantly, even if it's a tiny fraction, whatever your favorite fraction is in the martini. Vermouth is going to be a stronger flavor typically than the gin, so it's going to have a real role to play in the final cocktail. And so, but I don't know. I don't know how to, try out lots of different dry vermouths. I've never put effort into that, so I just go with the standard. Dolin is one of the standards. Noli Prat, the other standard. They're both fine. Martini and Rossi, I guess. So I don't know. If anyone in the comments wants to chime in saying what the best dry vermouth is I need to try, I'm happy to do that. Theo Lind says Friedrich Nietzsche was one of the first philosophers to be inspired by the findings of Darwin, and he believed that fundamental to life as well as to behavior was the Wille zur Macht. This will to power stands for comparison in his writings as separate to the term consciousness. For instance, in The Gay Science, Nietzsche wrote, consciousness is the last and latest development of the organic, and consequently also the most unfinished and least powerful of these developments. Is there evidence in the physical world of a will to power, and how does this philosophy stand to reason in arguments which dispute free will? Well, no. I don't think. I think that I wouldn't say that there is evidence in the physical world of a will to power. It depends what you mean. There's not a separate fundamental category, nor is there a separate fundamental category for consciousness. At best, these would be higher level derived categories in some emergent description, which is fine. I think the more relevant question is the concept of a will to power helpful when it comes to analyzing human beings and their preferences and behaviors and things like that? My suspicion, not having thought of it that much, I did supervise an independent study course with a couple of very talented undergraduates who wrote a paper about the will to power in certain contexts. So I know a little bit about it, but I think it's an exaggeration, right? I mean, I think that in some cases you have something that might be recognizable as that. In other cases, people have other motivations or other ways of thinking, and it's, a suggestion. I think that these kind of vague, hand-wavy kind of suggestions about, like, people are really all about X or Y or whatever. If they're any good, they capture some part of the truth, but never the whole truth, right? Maybe they give you an insight. Maybe they give you a lens through which to think about why people do certain things that is helpful to understanding certain actions in certain circumstances, but I think it would generally be wrong to take them too seriously as things that are inevitable or, single explanations for whole bunches of different behaviors. That would be pushing them beyond the point of usefulness. Brian Mendoza says, given the numerous studies linking weightlifting to improve neurological function, have you considered getting ripped to boost your intellect even further? Perhaps humanity's best chance of solving quantum gravity is only a few bench presses away. Well, I have to say, Brian, there's an implication here in the question that I am not already ripped. How do you know? I remember very vividly, there's a famous scene in The Good Place where Chidi, the philosopher character, who's been sort of this nebbishy, nerdy guy for several seasons, takes off his shirt and suddenly you see that he is totally ripped. And actually it was foreshadowed because Eleanor did mention, who was Chidi's girlfriend, like he is surprisingly jacked. You never know. So even though people dress in kind of philosopher outfits of sweatshirts and tweed jackets, who knows what's lurking underneath. But sadly, I would not classify myself as ripped, if I'm being perfectly honest. But I am a big believer in doing exercise. I do think that I'm not a dualist, right? If you're not a dualist, then you are correct, Brian, in drawing a link between how the body works and how the brain works. How could it be different? And of course, there's a link between how the brain works and how the mind works. So it just makes perfect sense that being in good physical condition would help you in your thinking. Now, of course, there's also downside. Like you have to spend time doing it, and maybe you could be spending that time thinking also. So I don't think it's at all obvious that spending lots of time in the gym or exercising is the optimal way to get your thinking done, but it probably plays a role in it. Overall, I think that both exercising and eating right are important to health and are things you should try to do. I'm actually better at exercising than I am at eating right. I'm not very good at eating right. I'm trying to get better, but I like food that is bad for me, and I like a lot of food, and so I need to cut down on that. If there's one thing that has been linked to living longer, it's eating less. Sadly, this makes me very sad. I don't want to admit it. That doesn't mean you should optimize the amount of time you want to live either. Like that's something that you want to get bigger, but you also want to have a pleasurable existence while you are alive. And maybe that involves eating some pizzas, So you have to balance all of these things the best you can. Eric says, I'm missing something about information. If one book was written in gibberish and another with equal amounts of ink and paper was a quantum mechanics textbook, and both were thrown into a fire, it would take the same amount of information to reconstruct them if the gibberish were constructed correctly. How can we quantify the additional information in the quantum mechanics book versus gibberish? What if, unbeknownst to us, the gibberish were actually an alien language, carrying even more insight than the textbook? Yeah, these are perfectly good questions. I talk about this a little bit in The Big Picture, in fact. There's a famous example of the Voynich manuscript, which I have a copy of. You can buy it from Yale University Press. It's not like I have a special copy. You just buy it on Amazon or an independent bookstore, if that's how you roll. The Voynich manuscript is this manuscript from a while ago. It's old, and it's famous because no one knows what it says. It's quite long. There's lots of pictures, and there's lots of text, or what looks like text, but it's a completely indecipherable alphabet. And this is very annoying to people who think that alphabets should be decipherable. Like, people have done studies on the Voynich manuscript, standard digital humanities type things, like counting the number of symbols that appear, the relative frequencies. And it seems, at the level of those analyses, to have all the characteristics of actual natural language, not just gibberish. But the pictures, the drawings, do not correspond to things that we know about. There's a lot of plants and things or animals, but they're not familiar plants and animals. So did someone just do all this work to make something that has nothing to do with reality? And is the work that they did a code? They write text in a known language and then translate it into their code that we haven't been able to decipher? Or did they just make up gibberish? We don't know. So the question about how much information is contained there is a perfectly legitimate one. But I also think it's a pretty answerable one. We had this conversation with Chris Adami on the podcast about biological information. And he made very clearly the claim that you should think about information as relative to something. One system has information about another system, okay? It's not just that information floats freely out there in the world as an objective quantity. It's a way of characterizing relationships between different systems. So Chris's point was that your genome contains information about your environment. Not because it knows what the temperature is and whatever, but it knows what kind of organism to build to survive in that environment, right? That's a kind of mutual information between your genome and the environment. So the question is there mutual information between that text and some feature of the outside world? And is that mutual information accessible to us? Do we know the decoding of it? And once you ask the questions carefully and precisely and define all your words correctly, I think everything makes perfect sense. Jeff B. says, my understanding is that from a Copenhagen perspective, when we observe a quantum system, it collapses to one of the possible superimposed states. But in quantum field theory, we are imagining superpositions of entire field configurations. So when we observe the system, why does it collapse to individual particle locations rather than an entire field configuration? Well, it depends on the observations you make. I mean, you have pinpointed something real and important. We're often very casual about how we talk about measurements in the context of quantum field theory. And that's usually because, as you might know, as you certainly know, if you've read The Biggest Ideas in the Universe, Volume 2, Quanta and Fields, when you have a field and you quantize it and you look at the low-lying energy states, it is perfectly okay to interpret those states as sets of particles. There are reasons why it's okay to talk about electrons and photons and quarks, even though we know that ultimately it's all fields underlying everything. And so if you have a situation, which you usually do, where your quantum field can be thought of as particles, then the language of particles is perfectly okay. You talk about detecting the particles and their positions and their momenta, and everything just goes through fine. But in general, if you have a quantum field theory, the thing you will observe is not a position of a particle as a general fact. You'll observe the value of the field, right? Now, if you think about it a little bit carefully, once you get into quantum field theory, you realize there's instantly a problem. What do you mean the value of the field? I could either imagine observing the value of the field at a single point that I pre-specify. I'm going to measure the value of the field at this point. Or I could imagine measuring the value of the field everywhere. Both are a priori perfectly legitimate questions to ask, but you soon realize that there are problems in both cases. The problems of measuring the field profile everywhere is that you don't have access to everywhere. You don't have any way to observe the field everywhere. So I can calculate the probability of getting an answer to that question, but I can't actually do the experiment. When I ask about measuring the value of the field at a point in space, the problem is that points are infinitely small. And you don't actually have the ability to measure infinitely small things. Even if you imagine doing it, the uncertainty principle would make you disturb the field quite a bit. And what you get as an answer might not be related to what the field was doing before you did the experiment in any obvious way. So we often, in those rare cases, physicists, are very casual about this, but sometimes they like to be more careful. So what we do is we imagine smearing the field. That is to say, I don't try to measure the field everywhere, and I don't try to measure the field only at one point. I take some region of space, or even better, some function, which looks like a Gaussian or something like that, a bell curve, right, where it's peaked somewhere and it kind of fades off near the edges, and I measure the field over that region. And that's something that is well behaved, and you can calculate and so forth. But, this is one of those areas of physics where getting it right, exactly mathematically rigorously right, is very hard, requires a lot of work and a lot of careful math. And the reward is at the end, you're like, yeah, you were fine. All the casual, non-rigorous things you did generally get you the right answer. That's not always true. A counterexample, a wonderful counterexample, is the Unruh effect. Bill Unruh, back in the 70s, trying to understand Hawking radiation, realized that if I had a particle detector that was being accelerated at a constant rate of acceleration, in empty space with literally nothing around, okay? In the quantum state that you thought of as the lowest energy state, the emptiest vacuum state you could find, that accelerated particle detector would see particles. It would detect particles even in empty space. This is called the Unruh vacuum or the Unruh effect. I talk about it in my general relativity textbook, Space-Time and Geometry. It's a feature of the fact that that detector is only because it's accelerating at a constant acceleration, there is associated with that detector, there's a horizon. There are parts of space that it is not able to access. And so it's cutting off part of the Minkowski vacuum state and is only sensitive to that. And if you take a pure state that is the vacuum and nothing going on, and then look at a subset of that pure state, a region of space, that's going to look like a thermal state, a state with a certain temperature and particles in it. What you see in the quantum vacuum very much depends on how you do the measurement. And this came back in the recent paper that I wrote with Chris Chaloux on what you see when you fall into a black hole. You have to be very, very, very careful about asking how you are doing the seeing. So anyway, the short answer is this is an answerable question, but you have to be very specific about the question you're asking and then very careful about calculating how to get that answer. Casey Mahone says, as someone who's done a lot of psychedelics, I want to take a shot at your question about how psychedelics can give us insight into the nature of consciousness. I loved Annika Harris's point about how people get confused between consciousness and self. Through psychedelics, I have dissolved the sense of I and expanded into the surrounding environment. It's difficult to describe, but it became readily apparent that while thoughts were being generated by the brain, there was also a there-ness that was ubiquitous. In other words, thoughts and the actions of neurons are not aware in and of themselves. They are merely being witnessed by the same entity that is witnessing any other person's thoughts. From the perspective of the entire universe, it is merely an illusion that one mind is separate from any other. That is key. The properties that make you separate from others in the environment are the illusions that Daniel Dennett discussed. But the thing actually doing the experiencing is a single continuous entity called the universe. Well, I don't know. I mean, maybe that's a claim that you can make. You can be inspired to make that claim on the basis of your psychedelic experience. The question is, how does that claim fit into a proper, complete, rigorous scientific understanding of the universe? And it may or may not. I honestly don't know whether or not that is a good way of thinking about the relationship between consciousness and the self and the universe. Maybe it is. But I would point out that the fact that you do psychedelics provides no extra data on what consciousness physically is constituted by. So it might very well, I'm very, very open to the possibility that doing psychedelics could help you understand consciousness in the sense that since it alters your consciousness a little bit, you get sort of a different perspective on how consciousness is working, where your thoughts are coming from, how they get sort of knitted together to make conscious experience. All that is fine. It's the underpinnings of consciousness in terms of physics or something deeper, if you're a panpsychist or something like that, that I don't think that you can get any insight into by doing psychedelics, because I can explain anything any experience you have on psychedelics can be equally well explained by a physicalist perspective or a non-physicalist perspective. So as a Bayesian, what you're supposed to do is have your credences, your prior probabilities, and then you update on the basis of information. But if the information that you get is equally well explained by the two different theories, then it doesn't help you decide on which theory it is. So again, just to be super clear, I'm totally open to the possibility that doing psychedelics gives you insight on the operations of consciousness. I don't see how it could possibly give you insight on the fundamental physical nature of where consciousness comes from. Jackson Race says, I'm sure you get this question often. What music are you listening to as of late? Any specific songs or artists? Is your head in a specific genre right now? Like I said, common question, but what an individual usually listens to changes from time to time. And what do you like about these songs/artists? Well, I'll be very honest. I think, like many people, when I was in my youth, music was super important to me, right? And I guess for me, as an undergraduate in college, was when music was most important to me. And I listened to the radio, and I thought very deeply about what to buy and things like that. As I grew older, music is less big a part of my life. It's still there. But so here's the thing. I don't drive very much. I don't spend a lot of time in the car. So that was one place where I would listen to music to a lot. And when I'm working, I'm a person who can't listen to music with lyrics while I'm writing or working, even just doing science, even if it's not writing. If there are lyrics, then there's a part of my brain that will listen to the lyrics that should be working instead. I can listen to instrumental music. I have a playlist of instrumental music that works sometimes for writing, but usually I don't listen to music at all. So the amount of music I'm listening to is less now than it used to be. So you should not take, I'll add the third ingredient here is that I cannot stand commercials on the radio. I respect it. I think that a radio station or an online streaming service needs to make money, just like podcasts do. So you have ads. I get that. But I would much rather pay to have my favorite albums downloaded into iTunes and just listen to them with my own favorite music without any ads. What that means is I get much less exposure to new music. And that's not as bad, that's not as frustrating to me now as it would have been when I was a college undergraduate. I think I know enough about the music I like, and so I'm completely ignorant about what is going on in music right now. I cheerfully admit that, okay? Having said all that, by way of preliminary, I can open up my iPhone and I can tell you the most recent albums I have downloaded, and I predict you will get nothing out of them. So here they are. Nefertiti by Miles Davis, Lateralis by Tool, Chicago 5 by the band Chicago, one song from Wings Over America, which is the live version of Maybe I'm Amazed, Gretchen Goes to Nebraska by King's X, GNX by Kendrick Lamar, and The Paris Session by the Touré Rachel Collective. There you go. Those are the albums I have most recently downloaded. So there's some classic jazz, some modern rock, some classic rock, and some hip hop. And the Paris Session is an instrumental duo. I don't know where I found them, the Touré Rachel Collective, but they're very good. I like listening to them. So there's no coherence there whatsoever. I'm a classic rock fan. I'm a jazz fan, but I like lots of different things. On my drive back, so on the drive up to New York City to drop off Puck, we were listening to Hamilton, the soundtrack, to get into the mood of going to New York, because the whole song about how it's the greatest city in the world. And then driving back, I was listening to Little Steven and the Disciples of Soul. Again, I don't know what conclusions anyone is going to draw from this, but that's the answer. David Maxwell says, in the 1990s, I wondered why the USA, a nation of two distinct and often opposing cultures, stays together. Now I'm wondering if it even can. Is it time to sever before each culture destroys the other, or one dominates? No, I don't think it's time to sever. And for that matter, I don't think the United States is a nation of two distinct and often opposing cultures. I think that it's a nation of many, many different cultures. Some are very, very close to each other, some very dissimilar, very hard to draw the boundary lines between where the cultures are, etc. I think that most countries have different cultural groups within them, and democracies manage to survive for quite a long time. Not forever, right? The United States has no guarantee of surviving as a democracy forever. It's already lived longer than average as a democratic nation, and it's been more or less stable in its boundaries, other than adding states here and there for quite a long time. But I think that not only is this situation where we have different cultures within the country more or less to be expected, But the practical difficulties of actually splitting the United States are completely crazily big. Like, there's just no way that that would actually work. Like, who gets the army? Who gets the nuclear weapons? Who gets the universities? Who gets the money in the treasury? It's just completely impractical to imagine doing that. I think that there's lots of things that would happen in the United States before that would ever be a serious consideration. Sid Huff says, you've noted that your Johns Hopkins appointment is a joint one between philosophy and physics. Also, on Mindscape, you've mentioned a number of papers you're working on or have recently published in the physics domain, as well as hosting Mindscape itself, which is heavily physics-oriented. Can you tell us more about what research you're working on in the area of philosophy? Do you have any papers in the works or recently submitted or published? Well, I have the emergence paper that I wrote with the Truth Parola that I've talked about before on varieties of emergence. Many of the papers I write in Quantum Foundations could be considered either physics or philosophy, so that goes either way. In the more pure philosophy vein, I do have various projects I'm working on somewhat slowly. I have one understanding causality in relating the arrow of time to causal networks, the kind of causal networks we talked about with Judea Pearl a while back. Another one in trying to better understand the anthropic principle, because like I said above, I think that people do the anthropic principle very, very badly. Another paper, a couple papers on the arrow of time, sort of a physics-oriented paper and a philosophy-oriented paper there. Something else that I'm forgetting right now, but, I don't sort of put them in baskets. I think I want to do the research that is interesting and the place that I can make a contribution to. If it happens to be more physics, happens to be more philosophy, then whatever. It's all good. I'm just trying to understand the world better one way or the other. Paul Brown says, I wonder if you could help adjudicate a jocular disagreement I have with a colleague of mine, let's call him Manu, who is also a Mindscape enthusiast. We work in healthcare. When he is chairing a meeting and a decision is needed on an issue where options have been debated and there is some difference of view, like is it okay to transfer a patient or not, he will say, okay, it's time to collapse the wave function. He says this in such a way that people usually get the gist, but I have 2 points of contention. Number one, it might appear pretentious and annoying to those few who get the context and befuddling to everyone else. And number two, I'm not sure it really works as an analogy. If you agree with me, Manu has agreed to stop using it. If not, I have agreed to no longer complain. Sorry to disappoint you here, Paul. I think that Manu is entirely in the right in this particular dispute. I use that analogy all the time, that we have to collapse a wave function here or there. Importantly, it is just an analogy. When we're trying to decide, like for the conference we're organizing in May, should we invite this person or that person? And we joke about collapsing the wave function because we don't know which one we're going to do. That's not really quantum mechanics going on. That's just uncertainty at the classical level. But still, the metaphor or the analogy or whatever you want to call it of going from a superposition of possibilities to one definite possibility is very vivid and perfectly fine. If some friends don't get it, then they need to read more books. I can recommend some good books that they can read. Anonymous says, it seems like retrodicting should get harder the further you get back in the past. But with past hypothesis, your ignorance about the state of affairs decreases the further back you go because entropy goes down and not by a little. So what is up with that? This is actually a really good question. And I think that, we understand a lot about it, but I don't know if we have like the fully quantitative understanding of exactly this picture. But the general idea is the following. The general idea that Anonymous is getting at is that a low entropy state, like we think the universe began in, is one that we know a lot about in some sense, in the sense that knowing the macro state only leaves us with a relatively small number of microstates that would fit into that description. So we know a relatively large amount about the microscopic arrangement of particles and things like that. So in some sense, if you just knew that, then your knowledge of the state of the universe is highest when the universe is lowest entropy. And as the universe increases in entropy, then the number of possible arrangements of the universe compatible with that knowledge goes up, and you sort of know less and less. But that's only saying that you know less and less if the only thing you know is the macro state of the universe that you would get from starting with the micro state and letting it evolve. But we know other things as well. We have data. We have memories and records of the past. That is to say, in the process of evolution from the early universe to now, there are things that happen that leave a trace, right? That leave some impression, literal impression sometimes, like footprints on a beach, okay? You can look at that. You can look at a footprint on a beach, and if all you knew were the laws of microscopic physics and statistical mechanics, the footprint on the beach wouldn't tell you that much. It probably just randomly fluctuated into existence. But the footprint on the beach plus your knowledge of the past hypothesis, your knowledge that the universe began with low entropy, allows you to conclude via reasoning that, again, has not been completely spelled out, but I think is, the basic outline is there, that there was a foot that was attached to a person, if it's a human footprint, that was walking down the beach. So the chain of reasoning that leads to specific facts about the universe, number one, is non-trivial, and number two, relies not only on the past low entropy state, which we didn't even know about when, 500 years ago, right? And yet we did know some things about the past. It also relies on present artifacts that we call memories or records or so forth. And there's a relatively complex interplay between these kinds of things that lets us say some things about the past and not others. And so the set of things that we know and can reliably say about the past is not either monotonically increasing or decreasing with era that we're talking about. It depends on a lot of details, like many things in the history of the universe. Okay, I'm going to group three questions together because they are very much of a spirit. P. Walder says, in your conversation with Annika Harris, she made a couple of asides to the effect that consciousness may not be causal. How could something without causal power create a felt experience in human experience? I find this puzzling, as pretty much everyone seems to agree. The consciousness is the one felt experience that we cannot doubt. And if it exists, doesn't something have to have caused the experience? Then Sandro Whitwer says, in the episode with Annika Harris, she proposes that consciousness might be non-causal. I'm having a hard time imagining a world where consciousness is a real thing and non-causal, but we're still talking about it. Am I missing something, or is there a logical contradiction? And then finally, Eric Runquist says, I've begun listening to Annika Harris's audio documentary, and one of her premises is that consciousness is a meta-phenomenon that doesn't have any causative power on the physical world, even on an organism's own behavior. I guess she thinks consciousness is just along for the ride. Do you agree with this premise? If not, what type of causative power do you think consciousness can have in a deterministic physicalist universe? So all of these are asking about the causal power of consciousness. I can't really speak for Annika and what she is trying to say. As often is the case when people are asking me questions about what guests would think beyond what we mentioned in the podcast, I'm a little bit reluctant to say what they would think. I can tell you what I think. I think that consciousness has causal power. Certainly my consciousness of certain experiences or effects seems to play a role in how I subsequently behave. For example, sometimes I can describe a conscious experience. The fact that I can describe the experience is good evidence that it has causal power because it has causally affected my description. Unless you think my description has no actual relationship to the conscious experience, then you think that consciousness is causal. Again, that doesn't mean that it's fundamental in any sense, right? It can be absolutely emergent. There's no implication that consciousness is part of the deep down fundamental architecture of the universe any more than tables and chairs are part of the deep down fundamental architecture of the universe. But they certainly have causal power. I can know that there is a table there. If someone throws a chair at me, I'm going to duck because I think that the chair hitting me would definitely have causal power on me. So that's all I can say. So I think I'm roughly on your side to the various people who are asking this question. Eric Davigi says, are international students having their visas revoked where you teach? 10 students here at the U of A have had theirs revoked, usually for idiotic reasons like they have traffic violations. I don't know what to do, and I feel like I'm getting radicalized as I just sit and stew and think about how the executive branch has been totally destroying the checks and balances system with its extrajudicial actions. I believe, if I understand correctly, that a number of students at Johns Hopkins have had their student visas revoked. I don't know of any who have been disappeared or deported or kidnapped like some others elsewhere, but I do believe that visas have been revoked, so it could happen. Indeed, I read a story not about at Hopkins but elsewhere about a student who was taken into custody by Immigrations and Customs Enforcement agents, ICE agents, and they didn't tell them that their visa had been revoked. And when asked why the student had not been informed that their visa had been revoked, it's so that ICE could arrest them. So they couldn't leave the country before they were captured by the authorities, which is exactly the opposite, and a very terrible opposite as it should be, and a really, really deeply despicable way of working. You change the rules so someone is violating the rules, and then you punish them for violating the rules without telling them that you changed the rules and that they were in violation, right? Because you just like putting people in detention or whatever. You should be radicalized by this. You should absolutely think that this is well beyond the pale, completely inexcusable. And, there's a feeling of helplessness that goes along with it because this is all happening and we can't stop it. But again, there is an accumulated effect. If many, many people complain about this and shout about it and raise a ruckus, that does decrease the chances that it keeps happening in the future. As someone was pointing out on Blue Sky just today, any political scientist who study this kinds of thing will tell you that there is a huge difference between what an autocrat can do when they have an 80% approval rating and what an autocrat can do when they have a 40% approval rating. And the approval ratings don't change because you snap your fingers. They change because you keep complaining and pointing out and refusing to go along with this, refusing to accept it as normal. And it's not just you, it's as many people as possibly can do that. So keep complaining, keep raising a fuss, keep telling your officials, the local media, whatever you can do, that this is not acceptable. It is not business as usual. We should not just go along with it. We should be constantly outraged and appalled by what is going on. Matt Haberland says, you've often said that the universe is accelerating. Is this a common abbreviation for something like the rate of expansion of the universe is increasing? Or is there another reason you prefer this phrase? There is kind of a reason. It is a common shorthand for what is going on, but the phrase, the rate of expansion of the universe is increasing, is actually not true. So that would be bad to phrase it that way. The point is that you have a couple of different ways to think about the expansion of the universe. One is that you have the scale factor, often written a as a function of t, and there is a curve that is the scale factor a as a function of t. And you might say, okay, what is the slope of that curve, which is a dot, which is to say dA dt, the rate of increase of a with respect to time. And then you might say, okay, is the rate of increase of A increasing or decreasing? So is a double dot, the second derivative of A, increasing or decreasing? And that's fine. And what is going on right now is that a double dot is positive. The rate of change of the rate of growth, the second derivative, is positive number, which means that it is curving upward, which means the universe is accelerating. If you think of A of t as kind of like x of t, the position of something as a function of time, then acceleration in the context of position means that the second derivative of x with respect to time is greater than 0. X double dot is greater than 0. And likewise, a double dot is greater than 0 right now. The reason for hesitation is that unlike position, the scale factor is not a definite number. There's a choice that goes into the scale of the scale factor. That is to say, there's nothing physical about saying a equals 1 or a equals 20 or whatever. It's only relative distances that matter. And so therefore, we create the Hubble constant, or the Hubble parameter, a dot divided by a. Okay? And a dot divided by a doesn't care about the overall scale of a. If you just change a by a factor of multiplying by 2, you change a dot by multiplying by 2 also, and it doesn't change the Hubble constant. So the Hubble constant is a real physical thing. The problem is that a double dot being positive doesn't mean that h is increasing. Indeed, h is supposed to be decreasing in the current universe because a is increasing and the rate of a increasing is going up, but so a dot is increasing, but so is a. So a double dot increasing with time does not mean that h is increasing with time. And indeed, h is decreasing. So the universe is accelerating means a double dot is positive, but if you said the rate of expansion of the universe is increasing, people would interpret that very sensibly as saying that the Hubble constant is increasing, which it's not. So you just have to be careful about what is meant. And summing it up by saying the universe is accelerating, I think is a simple way of expressing what is going on without getting into the mathematical details of what it actually means. Ken Wolfe says, in the upcoming Canadian federal election, many political parties are having difficulty finding any candidates at all to run for office. A career as a member of parliament does not seem to be attracting enough people to even fill all the seats. I am of two minds as to how to make this a more attractive choice. On my communitarian days, I want to promote government as not just a necessary but a noble enterprise that brings about the betterment of society and the advancement of civilization. On my libertarian days, I want to promote government as a simple administrative function that raises no more ill feelings than our choice of network service providers. Do you think there's anything to either of these institutions, or have I just missed the point? I think there's something to both of those ways of thinking about government. I prefer the first way better. I think that my libertarian days are driven by the realization, the admission, the simple fact that government is often inefficient and bloated and intrusive. These are all true things. But I also think that the government is simply best thought of as an expression of our collective will, right? We human beings in this society have certain things we want to do, like build roads or provide for national defense or educate the youth or whatever, that are better done collectively than individually because there is a common good that is being served by that. And the mechanism that we invent to do that is the government. So I'm pro-government in that sense. I think that the government serves absolutely a noble purpose. It often does it badly, but then the response to that should be to make it do it well, not to think of government itself as intrinsically evil. I think that going down that road leads to all sorts of bad things. So I think it is perfectly okay and indeed correct to cast service in the government as a noble thing that people should want to do, or at least be willing to do, for the betterment of society as a whole. Philip Ruthlin says, how should scientists balance the need for objectivity with the ethical and social responsibilities that often accompany research on contentious topics, particularly difficult and sensitive ones like intelligence difference between races or paradigm-shifting discoveries like Galileo's heliocentrism? Can scientific reasoning truly remain value-free, or is it inevitably shaped by societal norms and moral imperatives? This is a tricky question, of course, that people have debated a long time in many different venues. The way I like to think about it, which I think is roughly right, although there's probably details that could be better spelled out, is that the universe is objective. You know, what happens out there in the universe is completely 100% independent of the human mind, except in the cases where the part of the universe you're examining involves the human mind, of course. Then that's a different question. And therefore, the goal of science is ultimately to find a description of the universe which is accurate, and that description should ideally be objective. It should have nothing to do with human subjectivity. But of course, the goal of an enterprise and the practice of an enterprise are two very different things. When we do science, even though our goal is an objective description of objective reality, the way that we do it isn't objective at all. Some in very innocent ways and in perhaps non-innocent ways. We choose what questions to ask. We choose what methods to use in answering them. And as human beings, with our biases, we sometimes find answers that are found as much because of our biases as because of the reality of the situation. Pretending otherwise is just wrong, is just not doing science well or not understanding well. So I think that when you do research on contentious topics, particularly difficult and sensitive ones, like you say, you should strive even harder than usual to be completely objective and aware of your biases, right? Very often on these on these contentious issues, there's a side of the issue, depending on what the issue was, it might be one side or the other, that says, look, you have to pay attention to the science. You can't just pay attention to your feelings, which is true, all completely correct. But it is often used as a way of hiding the fact that science is done by human beings with their biases, and the science that actually is done by humans is not objective, okay? If you look at the bell curve by Charles Murray, this complaint that different groups have different, not complaint, but it is a political document as much as a scientific document. It tries to make the case that different groups have different distributions of innate intelligence, and political policy, social policy should acknowledge that fact. Okay, they couch what they say as objective science, but then you look at, you open the book and you ask yourself, are they going to acknowledge the fact that the claims they're making fall into a tradition of pseudoscientific claims that were clearly biased and clearly wrong? And you look at the book, and in fact, not only do they not acknowledge that, but sometimes they approvingly cite some of the historical examples of people just being racist in pseudoscientific ways. So that lowers your credibility in that purportedly scientific effort by quite a bit. So I think both that you should be free to do scientific research in any question you want, and you should be smart and wise enough to recognize that you're a human being and the other people working on this question are also human beings, and that means that we are all subject to bias and mistakes. Devin Bancroft says, I've read that in the very early universe, before some Higgs symmetry breaking, all the fundamental particles had no mass. Does this mean there were electrons zipping around at the speed of light? And if so, what happened to them when symmetry broke and they suddenly had mass? Yes, it does absolutely mean that, with one little footnote. The definition of what an electron was a little bit different before the Higgs symmetry broke. So when the Higgs was zero, all of the particles, many of the particles that we now know and love, not only electrons and quarks, but also the W and Z bosons, all these particles that we now know have mass, didn't have any mass, strictly speaking, before electroweak symmetry breaking. The strictly speaking is important, and that's actually maybe not even exactly correct. It's meant to flag the fact that when the Higgs before the Higgs got its vacuum expectation value, there was a non-zero temperature in the universe. So although the universe had no expectation value for the Higgs field, it did have a plasma of vibrating fields and particles all around it. And those affect the propagation qualities, characteristics of all the different fields. So it's kind of like you're in a plasma, the effective speed of light is not the speed of light, right? The speed of light that we know and love is, strictly speaking, the speed of light in vacuum, but in the air or glass, the speed of light is not exactly the same thing. That's why you get refraction and so forth. So the whole universe was like that before electroweak symmetry breaking. So in some sense, nothing was really moving at the speed of light. But you can think of the propagation of the electron field as a field that would be massless, but is now bumping into all the fields around it because of the thermal bath that it's in. Anyway, what I was trying to get to was the particles that we now know as the electron and the electron neutrino are two parts of a doublet they're related to each other, they seem very different to you and me because the electroweak symmetry has been broken. The electron has a negative charge. It has a relatively large mass compared to the neutrino. The neutrino has a very tiny mass and it has zero charge. But those differences are all because the symmetry was broken. When the Higgs had a zero expectation value, the 2 degrees of freedom that now we call the electron neutrino were still 2 different degrees of freedom, but they were completely identical to each other. So they had the same, what we call hypercharge. Before electroweak symmetry breaking, there was no such thing as electric charge in some sense because the symmetries, the charges were divvied up differently before the symmetry was broken. There was a full SU2 cross U1 symmetry, not just the U1 of electromagnetism. And what we call the symmetry of electromagnetism and therefore electromagnetic charge is actually a linear combination of charge under the previous U1, which is called hypercharge, and the SU2 that was unbroken at that time. Anyway, all of this is to say, there are a bunch of particles that in some sense were massless zipping around. What happened to them when the symmetry broke? Well, some of their energies were transferred to the Higgs field that is now absorbing a whole bunch of things in the vacuum state, and they slow down. That can happen, right? Just like a photon going from vacuum into glass will slow down. It's the same exact kind of thing. Just John says, priority question. I really enjoyed your discussion with Annika Harris. I've just finished listening to her latest audio publication entitled Lights On. I'm struck by the parallel concepts of what its likeness, aka phenomenological experience from the field of philosophy, and the concept of a frame of reference from physics. Please riff on this idea. I'm curious if some conceptual analysis applied towards these 2 terms of art could prove to be fruitful. Well, I don't know if I'm going to give a satisfying answer to this because I'm not quite sure. I mean, it sounds like you have in mind a parallel. You're struck by the parallel concepts of what is likeness and a frame of reference. I am not quite sure what the parallel is supposed to be. There is, of course, perspectivalism. There's the fact that individual agents have their own perspectives on the world. I see the world from literally a slightly different angle than someone standing next to me, right? We are literally looking at things in slightly different ways, and therefore we see slightly different things. That is directly analogous to frames of reference in relativity. It gets expanded kind of colorfully and metaphorically into saying that we have different perspectives on the world in a broader sense, which is maybe a little bit more loosey-goosey than the physics concept. But this perspectivalism is different, I think, than the what it is likeness of discussions of consciousness. There you're saying, I'm not exactly sure what you're saying. I've never exactly understood whether or not the idea of what it is likeness, as explicated by Thomas Nagel and others, is some well-defined thing versus just using a kind of casual phrase that we bandy about in everyday speech and acting like it is a well-defined thing. The what it is likeness to be a bat versus to be a human being is a little bit less quantitative and rigorous and precisely definable than the frame of reference that you have in physics. Furthermore, the frame of reference idea in physics is based on the next statement that you make, which is that the laws of physics are invariant under choice of frame of reference. The way that you look at the world, the angle you take on it, the velocity that you're moving with respect to it, etc., affects what you see and what you experience, but it doesn't affect the deep down dynamical laws that govern how the universe works. That's the basis of the theory of relativity. I'm not sure what the analogous thing is supposed to be in the case of what it is likeness in studies of the mind or awareness or consciousness. So I think that one of these ideas is very well defined and very understandable. The other is a little bit hand wavy. I'm not quite sure how much of an analogy I would want to draw there. Richard Cashdan says, in a previous episode, you mentioned something about a dark matter particle in your glass of milk. If dark matter is composed of particles that have no interaction with ordinary matter, except for gravity, then if a dark matter particle was in your milk, wouldn't it immediately fall through the milk and the bottle and just fall to the center of the earth like a neutrino? Yes, of course. I'm sorry, that was my fault if I didn't make that clear. on average, if the dark matter has a mass of, a few hundred times the mass of the proton, which is a reasonable area for it to be in, although we certainly don't know for sure, that's just one of the reasonable guesses, then you can calculate from the inferred dark matter density in the solar system what is the average number of dark matter particles per cubic volume of whatever kind. And what you find is that in about 1 cup, there's about 1 dark matter particle. But that's just an average statement. That doesn't mean there's literally a dark matter particle that is stuck inside your cup. In fact, like you say, dark matter particles don't interact very strongly with ordinary matter, so they just move right through. And the typical velocity of a dark matter particle is around 300 kilometers per second. So it moves through very quickly. So every second, there's many, many, many dark matter particles both entering your cup and then leaving. They're not sticking around for any reason. Going to group 2 questions together. Michael Bright says, would you have interest in going to space on something like a space tourism rocket? Assume cost was not an issue. Say all of us Patreon supporters chipped in to make it happen. If you would have interest, what intellectual insights or emotional response would you hope to have? And then Nick B says, Perry and Sanchez on Blue Origin. Giant step for womankind or more vacuous than the vacuum? So not exactly the same question, but both questions about space tourism. I think space tourism is fine for people who want to do it, who have that money. As I've said before on other podcasts, I think that people at that level of money should be heavily taxed. But if they, after taxes, still want to use some of their money to fly up into space, then good for them. I'm not especially drawn to the idea, like a little bit drawn to it. Like I can see the romance, the adventure of it, and so forth. If I had that much money, I would probably do other things with it. It does seem a little bit frivolous to me. And also, I have very low confidence in the companies that are doing this. Going into space is not super duper safe, and we haven't had an incident yet that I am aware of where space tourists have died in an accident. But we haven't had that many space tourists, and it's going to happen one time before too long. And I have too many things I want to do in the rest of my living days to waste them by mistake on a rocket ship that I don't completely trust. Of course, we think that our technology gets better and things should become more safer. But with the proliferation of different companies sending people into space, there is a temptation to cut corners. We've seen that with Boeing and good old ordinary airplanes, right? Like we have the technology to make airplanes almost completely safe. And Boeing, for various reasons, has decided to cut corners and not do that. And we've had accidents as a result of it. I don't have any faith or confidence that current space tourism companies are completely reliable. So I would worry about that. In terms of Katy Perry and the recent Blue Origin flight, certainly I don't think that this is any victory for women in particular. I mean, these people were tourists. They were passengers. It doesn't take great courage or bravery or intelligence or anything like that to be a passenger on an airplane or a rocket or anything like that. Maybe there's some inspirational aspect to it where some young girl, sees that and thinks that, okay, that could be me also. I'm going to become a real astronaut. That's absolutely possible. Just like if you have an inspirational character in a movie or something like that. That playing an inspirational character in a movie doesn't mean that you, the actor, has actually done anything inspirational, but nevertheless, you can have an inspirational impact on the world. I'm not quite sure if that particular stunt has a lot of inspirational impact on the world, but maybe it did. Mostly, I think it was supposed to be publicity for Blue Origin. And again, I think that the money could have been much, much better spent on other things in the world. Tim Converse says, I've been thinking about your argument that physics is complete as far as everyday human scale phenomena are concerned, that the core theory is all you need. Even if that is true now, what's your credence level that will continue to be true for, say, hundreds of years of human invention? If future inventions used in future everyday life exploit more exotic physics, will the core theory of 2025 still have them covered? Well, so there's no such thing as the core theory of 2025. The core theory is the core theory. It's not dependent on time. It's not like that there was a core theory in 1925 and there's a different one now. There's a theory right now, which we have called the core theory. It's not the complete theory of nature. We will get better theories. 100 years from now, we'll have a better theory, but it won't be the core theory. It'll be some better theory. And likewise, what I have called the everyday life regime doesn't change with time either. Of course, it's possible that we might be able to invent things using physics beyond energies and beyond, distances or timescales that are currently accessible to us that might give us better technologies. That's possible, but you would have to go outside of our currently defined everyday life regime, okay? So it would involve, energies of much higher energies than we can build at conventional particle accelerators, for example. If you could imagine a way to pack more than a Large Hadron Collider's worth of energy into a pocket-sized device, and you somehow found that physics that was manifested by doing that was technologically useful, then I do not have an argument that that's impossible. It seems unlikely to me, but it's not impossible, certainly. So the argument that I have doesn't cover those sorts of cases. So, the argument I have, I'll say it over and over again, the physics underlying our everyday lives is completely known right now. Of course, people's lives might change, but the regime of physics that is called the everyday life regime today is a fixed thing. It might not be the everyday life regime in the future, but it is a convenient label for a regime of physics that we do completely understand in physics right now. Rich Murphy says, supposing you were considering donating money toward scientific research, would you A, give a lot of money to a few research projects, perhaps even just one, B, give a little bit of money to many, or C, something else? I realize this is exactly the set of question dealt with by NSF and other federal funding agencies, but given current events, perhaps civically minded individuals will do more to make up the gap going forward. How should we be thinking about this? Well, I think there's a couple things here. I think of at least three things I need to say, so hopefully I keep them on my brain as I'm trying to answer the question. One is I think you need a distribution. I think that probably the proper scientific funding portfolio involves some big research projects that can't be done without all that money, as well as many smaller research projects where you can make progress with much less investment. That's probably what I would think is the proper allocation. But number two, you have to actually look at the specific research projects. You can't just abstractly think about the funding allocation for something like LIGO or the Large Hadron Collider or the James Webb Space Telescope. It's not just that, okay, we're going to do a couple big research projects, let's do these. It's specifically a scientific case that is made that we want to do a certain thing, like, let's say, detect gravitational waves from black holes a billion light years away. And the point is, if you have, I don't know what LIGO cost, a few $1 billion, okay? So you have a few $1 billion to spend, and you say, should I spend it on building LIGO, or should I divide it up into 1,000 pieces and do smaller things? You have to balance that, of course. That's a question you should ask, but you should recognize that dividing up into 1,000 smaller things won't detect gravitational waves. There's just zero way to do that, at least as far as we know, right? If you want to do that science, you got to spend that much money. Likewise for the LHC or JWST. So maybe you don't want to do that science. Maybe you don't think it's worth it, but you don't do big science projects just because you think this is my favorite science project, let's do that. It's because you say, I can't do this science without spending all this money. If I can do equally good science by spending less money, then I should do that, right? Because then you could do many more projects. And the final thing to say is that I am very much against thinking that we should expect private, civic-minded people to step in and take over from the federal government in funding science. I mean, there is plenty of of private funding, foundation funding, et cetera. It's very important. I'm in favor of it. I am just not in favor of thinking of it as replacing government funding. And for exactly the reason we just talked about in the Canadian election question, how should we think about the role of government? An individual or a foundation or whatever is perfectly allowed to say, I think this is cool. I'm going to fund this, right? And that's what individuals always do. They don't just turn over their money to the experts and say, where do we get the most impact? They almost always have directions from their founders or funders or whatever about what kinds of research they want to push forward. And that's completely okay. Whereas the government is literally supposed to represent our collective judgment. So the government has a responsibility that the individual foundations don't have to try to be fair, to try to do as much broadly based science as they can think how to do, and to judge different scientific proposals against each other in the minds of experts who are qualified to judge them. So that's what we really need. That's what most scientific funding should be. You know, as terrible as it is that the government is being dismantled by treacherous agents and scientific funding is being decimated, we can't lose sight of the fact that it's still the right way to do it, and we need to rebuild that rather than replace it. Richard Graff says, when people ponder why we don't see intelligent life elsewhere in the universe, they tend to assume intelligence is a logical outcome for evolution to pursue and conclude we don't see it because its complexity makes it hard to achieve. But there's another assumption I think is as likely. Intelligence isn't necessarily a good survival strategy from an evolutionary standpoint, especially given the high cost of achieving it. Rather than being an outcome evolution always strives for, it's another of the many tools in its toolbox, and a relatively rare and minor one at that. Do you give this assumption much credence? Well, I wouldn't put it exactly that way. I mean, I think that all else being equal, I think one can make an argument that intelligence in an organism is evolutionarily beneficial, because intelligence gives you another way to exploit the opportunities around you in the environment vis-a-vis food or shelter or reproduction or whatever it is. But usually all things are not equal, okay? Like you say, there are costs to achieving intelligence, and maybe those costs are not worth it. So I wouldn't say it's that intelligence isn't useful. I would just say that maybe evolution finds easier ways to do things sometimes. That's completely possible. But, you know, also I would recommend avoiding phraseology like an outcome evolution always strives for. Evolution doesn't strive for anything. Evolution just plays the field. It tries a lot of different genomic combinations in the space of possibilities and sees which ones work. Okay, there's no teleology about it. And when it hits intelligence, intelligence seems to be a very good survival strategy as far as I can tell. Krzysztof Radomski says, how would you argue with someone who says that science doesn't matter, or the state should donate only scientific research which has real-life applications? That intuitively excludes, say, quantum physics, origin of life, paleontology, exotic mathematical theorems, etc. I know that you, among many other science popularizers, do that all the time. But let's say you have a little time and someone wants you to convince you with a short, condensed argument or example. Obviously, people who do not trust science will not read scientific books nor listen to podcasts. So first, I don't think it's obvious, that last bit at the end. There are plenty of people who don't read scientific books nor listen to podcasts, but that group is not fixed. There are people who can come in and out of that group. So I don't think you should ever just give up on large groups of people. You should attempt to reach out to them as best you can. But to the question, my attitude about this is always that you should be honest. There might very well be scientific research that ends up having no tangible impact on human lives. Number one, we don't know what that research is. You don't know whether there will be an impact or not until you do it, and it might take a long time to figure out what the impact might be. That's the whole point of basic scientific research. And as another separate argument, that's why universities are good at doing it rather than more short-sighted, profit-oriented corporations, because universities can take that longer view. Number two, even if you knew that it wasn't worth doing in terms of economic or medical or technological payoff, it's still worth doing because I want to know the answer. And many other people want to know the answer. There's plenty of people out there who are just curious about our world. To say that it doesn't matter unless there is some tangible economic improvement is to say that most human activity doesn't matter, right? No art matters. No sports matter. TV shows don't matter. They don't, make you economically more well off. These are things you do with your time. Everyone should just eat the minimum number of calories and protein and vitamins and not actually enjoy it. it, right? I think that life is worth enjoying, and I think that curiosity and understanding the world better is part of that enjoyment. And that's the single biggest reason to do scientific research. Kyle Stevens says, well, when you were thinking about more abstract ideas in physics, what's going on in your mind? For example, when thinking about the Higgs boson or other high-energy particles, do you have some sort of mental image of these particles, or is your conception more abstract than that? I think that different people are probably different than in the ways that they would think about these things. You know, you might have been aware of this fact that some people are really good at visualizing in general, right? Like visualizing an apple or a face. And other people, even people who are successful artists, sometimes have almost no visual field popping up when they're just imagining things. They can look at things fine and they can see them, but they can't summon up an image in their heads. So I suspect that scientists similarly have a wide variety of different ways of thinking about things. I think personally I try to balance things. You know, I'm a relatively visual person. I like diagrams more than equations, but you need the equations, absolutely, especially when your diagrams, when the diagram you want to draw is of a 10 to the 100th dimensional vector space. You're not going to do that, right? Or even a single vector field, the electric field throughout space, you're not going to draw the value of the electric field at every point. So you have to simplify, and you have to model, and you have to have toy models, and you have to have examples and things like that. So very often we think of a 10 to the 100 dimensional vector space as a 3-dimensional vector space, because that you can imagine visualizing. We draw a vector field with just a couple of arrows to sort of give you vaguely the impression of what is going on. But also you need the equations at some point to derive in a trustworthy way what your theory predicts. You have to posit what your theory says in terms of equations and then manipulate the equations mathematically in a reliable way. And that's going to be the answer. You can't simply go on the basis of the pictures in your head. So I like to go back and forth between them, and eventually you end up at hopefully a useful answer. Nandi Nobel says, is consciousness ultimately at risk of permanent and complete eradication? In a reality where climate change and potentially AI going rogue are ingredients, should we consider consciousness itself being at risk? I understand these risks aren't immediately imminent, but from the perspective of materialism in a universe where we are not aware of consciousness other than on the planet we inhabit, what is a valuable and meaningful stance and view in regards to this idea? Well, sure, it's possible that consciousness would be eradicated. I think that you have to be thoughtful about these things. One aspect of being thoughtful is admitting the possibility of events that are unlikely, but nevertheless would be disastrous if they happened, and taking those possibilities seriously. We human beings are not good at that. We're not good at even dealing with risks of things that happen only once every 1,000 years, right? Our lifetimes don't last 1,000 years, so our brains just don't work that way to deal with those risks. Frankly, we're not even used to dealing with risks that are happening on a 10-year time scale, for that matter. So you actually have to apply your rationality a little bit. But it's hard to apply your rationality, and in particular, it's very hard to take uncertainties into account. It's very, very hard to accurately judge the credence you should put on one of these very big risks happening. And so some humility about acting on the basis of your estimates is also called for, right? You don't want to turn all of society upside down just because you personally have become convinced that there is some big risk out there that no one else is convinced is worth taking seriously. So I think that actually the best thing to do is to take big risks very seriously, but actions that we take to ameliorate them should be relatively small scale and manageable, right? So instead of saying right now, oh, AI could go rogue and take over the world, let's just worry about like the short scale, much more believable and imminent risks of AI spreading disinformation, of AI taking over control of crucial infrastructure or weaponry or something like that. All the much less dramatic things. If we can't even control them, then what in the world are we doing worrying about AI taking over the world? And in trying to control them, I think that we have a better chance of judging accurately what the bigger risks actually are. For climate change, we know a lot. It's very different than the AI thing where we're just sort of science fiction-y imagining what could go wrong. For climate change, we know what could go wrong, and it is going wrong, and we also know how to stop it. We just don't have the willpower to do that. So I wish we did. And again, I think that there's small things that we can do, but in something like climate change, the scope of where the danger is coming from is so very broad that wide-scale government interventions are much more obviously the only way to do it. If you do recycling of your bottles, that's great, but it's not going to solve climate change all by itself. You actually need government scale regulations to fix things. And we know that. That's not something that is unknown, so we should go ahead and do it. So I think all of these risks you should take seriously. Even if they're small, the risk is important enough, you should take it seriously, but you have to take them individually, piece by piece, and judge them on the basis of what we know and what we don't, and how to approach them with as little bias as we can, but also as much humility as is required. Ed Said Stuff says, electromagnetism is quite a bit stronger than gravity, yet significant concentrations of matter or gravity cause general relativity to fail. Are there any examples of significant concentrations of electromagnetism causing GR or any other well-established theory to similarly fail? If there are no examples, do you think it is theoretically possible? Well, I think I get where you're coming from. Gravity is a weak force, yet we can imagine things like black holes where the force of gravity is completely impossible to resist. Why don't we get something like that with electromagnetism where the force is much stronger? The answer is that gravity is always attractive. Even though gravity is weak, it builds up, right? The more particles you have, the more atoms you have in your planet, the more gravity you're going to have. That is not true for electromagnetism, where there are both positive charges and negative charges. So to get something like a singularity in a black hole requires a lot of mass and energy in a small region of space. To get something analogous to that, you would need to have a lot of positive charges, or at least same-signed charges, either positive or negative. Pick a sign and put those into one very small region of space. And guess what? You can't do it because like charges repel in electromagnetism, unlike they do in gravity. So the situation is just very different. And of course, if you have electric fields or something like that are near the Planck scale, then because gravity is part of the game, you're not going to have a complete explanation. And there's also, even in QED, quantum electrodynamics, there's an energy scale well beyond the Planck scale called the Landau pole, where quantum field theory effects make the theory break down. But in the usual way, ordinary way of thinking about things, it's actually interestingly easier for things to go wrong in general relativity than they are in electromagnetism. Anonymous says, I just survived another life-threatening health problem this past week. And in addition, I received an implant that will prevent similar health issues from escalating to become life-threatening again. The number of times I've survived is now in double digits, and I'm still pretty young. I don't go out of my way to test quantum immortality. Still, I've started to wonder if I am alive and well enough to ask a question, because that was possible in some branches of the universal wave function, and in all others it wouldn't be. How should I think about quantum immortality? The comic book multiverse seemed to me very different than the quantum mechanical one. I'm not someone who thinks that quantum immortality is an interesting thought experiment. I think it's just a wrong way of thinking based on the idea that, I should only care about my existence when I'm alive to care about it. Even though I'm alive today, I care about whether or not I'm going to still be alive a year from now or 10 years from now. Even though if I'm dead 10 years from now, I won't be around to care about it. I care about it now. And I think the exact same thing is true about quantum immortality. I don't think that the argument that you will live forever on some branch of the wave function is in any way supposed to make me feel better. I also don't think that if you have events happening to you and you seem to survive them, and there is some element of luck to it, that you should necessarily or even probably reach for a quantum mechanical explanation. whether or not you have quantum mechanics, whether or not Everett is correct, you still have the fact that there's a selection effect. You're only talking about this experience and asking questions about it if you survived, right? So there's no other way to have this conversation than to be the one that survived. It doesn't mean that there are other copies of you that didn't survive. That's just not any part of the argument. So, think what you will about life-saving operations and so forth. Don't expect, I would not invoke quantum mechanics or many worlds to help make sense of it. Brandon Lewis says, when I was younger, I couldn't wait for computers and the internet access to become ubiquitous. Lately, I've begun to feel that perhaps the internet in general, and smartphones in particular, were a huge mistake. I'm no longer confident that the obvious benefits outweigh the obvious downsides, and I don't think we're overall happier for having embraced it. Sure, the internet has improved access to information, but most of it is total garbage. At the very least, I think the economy was far more diverse and interesting before the internet than it is today. Do you think we're better off in some hypothetical world where the internet had failed or never been invented? I don't think we are, but I don't know for sure because the story has not yet been completely written. After all, if it were not for the internet, you'd not be listening to my voice right now. I would not have this podcast, right? My life would be very, very different. I met my wife over the internet we read each other's blogs, right? So I can't possibly say that the world would be better off if it weren't for the internet. Of course, any new technology also leads to new possibilities of exploitation, right? We talked about that with Daron Acemoglu. I talked about it on my solo podcast on the coming singularity. It's absolutely a fact that when you develop new technologies, you can do good new things with them. And also you can squeeze the world for a little bit more extra value that goes into the hands of a small number of people. And sometimes the incentive structure is lined up in such a way that a technology that could be used for good gets up being used not even just for evil, but just for, a relatively random motley collection of good and bad purposes like the internet is. I like the internet. I spend a lot of time on the internet. I use it all the time. That doesn't stop me from acknowledging its downsides that are very, very real. The fact, look, we could quit it if we wanted to. We could turn it off, the internet, tomorrow. There's very, very strong reasons not to do that. And that, to me, means that probably overall it's a good thing, but maybe we're just fooling ourselves. David hates entropy. I don't know why you would hate entropy, David. Entropy is very important. Asks, do you think democracy can continue to thrive in a technologically advanced society without a critical mass of voters and politicians who are good Bayesians with the ability to update their views based on new information? It's a good question. As I said already, this podcast, and I've said many times before, I don't think that the point of democracy is to imagine that human beings are perfect reasoners or even that they are perfectly good at expressing their own self-interests, right? Because they're clearly not either one of those things. But I think that human beings are better judges of their own individual values than other human beings are. And I think that's the basic argument in favor of democracy. But democracy can fail or democracy can lead to bad outcomes. And so you would like your citizenry to be good at it, good at being citizens of a democracy. What does that mean? Being well-informed, being good reasoners, being good Bayesians, I suppose. I think updating your views based on new information is an important thing, but it's certainly not the only aspect of what you want to go into this. So I wouldn't put it in those terms just because I think that the set of things you need to be a good citizen is much broader than being a good Bayesian, but I would be happy to agree that being a good Bayesian is one of the things that contributes to being a good citizen. Rad Antonov says, the recent DESI dark energy result updated the limit on neutrino masses. Mark Kamikowski thought that was important. And last week, Katrine reported results from beta decay measurements that set a direct limit on an antineutrino mass. Fortunately or not, there is no sign of tension. How far do you think the explanatory power of physics theories should extend? Specifically, should a theory of everything, if one exists, be able to predict the masses of fundamental particles, such as neutrinos or perhaps of composite ones like protons and neutrons? I don't know. I have no idea how far the explanatory power should extend. We're going to have to take what nature gives us. I mean, it depends what you mean by explanatory power. Does the standard model of particle physics as we currently understand it explain the mass of the electron. I mean, it's a number. It's a parameter in the theory. I think we have zero right to demand that there is some other explanation other than a brute fact for the mass of the electron. We can hope that there is. We can spend our scientific research time looking for one, being optimistic that maybe we'll find one, but we can't demand it, and I don't know how much we can expect it. We'll have to wait and see. Happily, we're not on the precipice of finding the theory of everything, so we can have that optimistic stance for a little while longer. Johann Yartelius says, so Mark and I were talking the other day about the universe and the cosmology as we do. Standard candles came up, and we realized we need to know more. I think we get the gist of how they are used and how we can use perceived brightness to infer actual brightness, but how can we be sure they are standard? We'd like to understand them better. Could you shed some light on this? Sure, this is a very, very, very important topic in cosmology. The cosmic distance ladder relies on standard somethings. That is to say, knowing either the size or the velocity or the brightness of something very far away intrinsically. And then you can use just geometry and general relativity to figure out the relationship between the distance and what you actually see. So there are luminosity distances, which you get from standard candles. There's also angular diameter distances, which you get from something like baryon acoustic oscillations that we talked about. If you know a standard angle, a standard size, basically, then you can convert angle into distance. So for standard candles, for anything really, you build up this cosmic distance ladder in pieces. This is worth a whole podcast by itself, but if you Google cosmic distance ladder, actually Terry Tao, the mathematician, is interested in this topic, and he's given lectures on it you can find online. You start with literally simple geometry. You start with parallax, right? You start with the fact that as the Earth moves around the sun, nearby stars shift slightly in their positions because of parallax, and that's just geometry. So you can find the distances to nearby things, very nearby things. And these days we can do much better. The Gaia satellite gave us a map of proper motions, which is to say the velocities of and parallaxes of many stars throughout the galaxy. So we can get a lot of real physical distances without any assumptions. And in the galaxy, you can find certain kinds of stars whose brightness you can calibrate. Cepheid variables are famously this. Henrietta Swan Leavitt taught us how to see the relationship between the period of a vibrating Cepheid variable star and its brightness. And you can do that by looking at stars that you know are close to each other, like they're in the same cluster or something like that. And from that, you can get a relationship. So it's not quite a standard candle, but it's a standardizable thing. It's not that all Cepheids are the same brightness, but if I know the period, I know the brightness. And some Cepheids are bright enough to see in other galaxies, so you can calibrate the distance to other galaxies. And then you can sometimes see supernovae in those galaxies, and so you can calibrate the distances to those supernovae. And then if there's different kinds of supernovae, there's type 1s, there's type 2s, etc., and they have different light curves and different spectra, so you can tell them apart. And it turns out that for type 1a supernovae, again, they're not standard candles. They're not all the same brightness, but there is, again, a relationship between their periods. They don't oscillate, but they have a period of increase in brightness and decrease in brightness that is correlated with their maximum brightness. So they're standardizable candles. So the answer is we don't know ahead of time the brightness of a certain supernova very far away. But we can figure out the relative brightness of the supernova and a Cepheid variable, and then the relative brightness of a faraway Cepheid and a nearby Cepheid, and we can get the distance to that using just geometry and parallax. And that's how we build up the cosmic distance ladder. Then, of course, you need to wait around for a supernova to happen in a galaxy, but modern technology gives us lots of supernovae on demand. In the 1990s, that wasn't true. In the early 1990s, you just had to be lucky. By the late 1990s, we had figured out ways, and we built the telescopes to harvest many supernovae, and that's what allowed us to discover that the universe is accelerating. Andrew Jewell says, it is generally accepted that the universe began some finite time ago, starting at a finite size, and has since been expanding at a finite rate and is thus finite now. However, many experts think that the universe might be infinite. Clearly, I am wrong about some of this, but I don't know which part. I hate to tell you, Andrew, you are wrong about many parts of this. So you say the universe began some finite time ago. I'm going to let that one slide. The known universe began at the Big Bang about 14 billion years ago. There could be a universe before that we don't know. There's a lot about the universe that we don't know. When the universe started in the Big Bang model, was it finite size? That we have no idea at all. It is completely possible to have models of the universe where when the universe exists, it is always infinite in size. Even if it had a beginning, it could begin infinitely big. That is completely 100% conceivable. Or it could have begun with a finite size. That's also possible. To be honest, even the question, does the universe have a finite size or infinite size, is not well defined in general relativity. There are different ways of slicing space-time into slices of constant time that we call space at one moment in time. And for certain global geometries of space-time, you could slice the universe equally well into slices that are infinitely big or only finitely big. I know that's tricky. It's hard to visualize in your head, but trust me, it is true. So it's not even a well-defined question. But also, many of the discussions that you will hear about the universe and cosmology are based on the idea that the universe is simple in some sense. The universe that we see, our observable universe, which is finite in size, but that's just because we don't see the whole universe. The universe we see seems simple in the sense that it is on large scales, homogeneous and isotropic. That means there's not that many possibilities for its geometry. The large-scale average geometry is either positively curved, negatively curved, or flat. Those are the only choices. But beyond what we can see, there's no reason to think that the universe must still be simple. It could be wildly different from place to place. So all of those sort of classic discussions of the universe as a whole are making a huge, completely unfounded assumption that the universe, as we see it, just extends on forever. We just don't know whether that's true. So when it comes to the parts of the universe that we haven't seen, either because they're too far away or because they're before the Big Bang, I advocate just saying that we're not sure. All right, I'm going to group two questions together. John E. says, we've built a 27-kilometer collider in the Large Hadron Collider. What would be required to go to the next level and being able to test things like string theory? Just a bigger collider or something different altogether? And Paul Conti says, regardless of whether the USA participates due to current budgetary and political constraints, do you think that the proposed new and much larger super collider at CERN is worth the huge cost? Would such a budget perhaps be better spent building a radio telescope plus other telescopes, detectors, and instruments on the far side of the moon, for example, given that such a project would probably take no longer than the construction of the new super collider? Well, we have had podcast episodes about both of these scenarios. We talked with Kari Cesarotti about the possibility of a new collider. We talked with Joe Silk about the possibility of telescopes on the moon. So you're welcome to listen to the science cases for those and judge for yourself. As is hinted at in the question, the United States is not going to be a leader in any of these things right now. We're canceling the telescopes that we halfway have built already because we're being idiots about this right now. So I'm not very optimistic. I don't think it's right. Well, I guess I don't know what to say, to be completely honest here. On the one hand, these are not competitors. We don't have a fixed amount of money and saying, okay, we're either going to build a telescope on the moon or a large particle collider. I would like to at least aspire to do both of these things because they're very worth doing. And, the timescale for doing these is decades, right? It's not like we're spending all the money all at once. On the other hand, at some level they are competing because there's a finite amount of money in the world and you can't do everything you want to do. It would be a shame if we had to choose between them because they're just completely different kinds of things. So rather than comparing a telescope on the moon to a larger collider, I think it's worth just thinking about the idea of a larger collider for its own sake. There's a well-known fact that we were all hoping to find a lot of new particles at the Large Hadron Collider, and we didn't. We found the Higgs boson and nothing else. So what will be at the next thing that we might want to shoot for at a different collider? This goes to Johnny's question as well. And the answer is we're not sure. We thought with the LHC, or with the superconducting supercollider before it, that we had a well-defined target, the energy scale near and above the Higgs boson mass, the energy scale characteristic of electroweak symmetry breaking. We thought it wouldn't just be the Higgs boson, there'd be something else there. So far, we haven't seen anything else there. And so if that's not there, if we were just wrong in our expectation, there's certainly a defensible attitude that says we have no target to shoot for just beyond that. Now, coincidentally, just this week, I heard a seminar by Michael Peskin of SLAC, a very respected particle theorist, who points out that there is an argument that there can be new physics literally 10 times the energy of the LHC. Namely, that if you still want to explain the value of the Higgs boson and electroweak symmetry breaking, rather than just positing it, right? Like if you want to have a mechanistic explanation for why it is that number, there's numerology you can do that makes it quite plausible that such an explanation should fall somewhere in the range of 1 to 10 times the energy of the Higgs boson itself. So a new collider with 10 times the energy in the center of mass would just about do it. You can argue over that kind of logic, but I think it makes sense. It's not completely made up. So there are reasons to think, given that we haven't found what we were expecting at the LHC, to think that a little bit more energy would be helpful in finding new things. So I do think there's a case to be made on physics grounds for building a new collider. I don't have the expertise to judge what is the best strategy among the various different kinds of machines that have been proposed, muons or protons or electrons or whatever. But I do think it's worth doing. It's certainly worth doing the sort of telescope on the moon kind of things. There's obviously very large technological questions to be worked out there, but these are both long-term projects and worth doing. So I think that the question, I think that the science cases are pretty easy to make for both of these kinds of projects. Whether or not we will have the money and the political willpower to do them, I have no idea. Tom says, as an NBA fan, why do you think American sports leagues are so allergic to promotion and relegation? Almost all other major sports leagues in the world have a real pyramid system. It seems like this should ensure high quality in the top league and add some excitement to the latter stages of the season. I can see the argument for it. To be honest, since I am an American and no sports leagues in America have this system, I'm not that familiar with how the system works. I don't think as a practical matter it's likely to happen anytime soon. For those of you who are not here in the United States, the way that baseball, football, basketball, hockey all work is that there's simply one major league and teams stay in the major league all the time, no matter how well or badly they do. There's no danger of being relegated to a minor league. There's also minor leagues, but the teams that are in the minor leagues just stay there forever. These leagues are treated as very separate things. They have different kinds of stadiums, different capacities, different fan bases, different ticket prices, different salaries. Everything is very, very different. It would be very, very difficult to change the system in midstream so that teams could go back and forth between the major leagues and the minor leagues here in the U.S. So I don't think it's going to happen. Whether it should happen, I actually don't know. I think that the argument could be made, that in my favorite league, the NBA, teams that are bad have this huge benefit from the NBA draft, where they get to pick first in the NBA draft, and they get high draft picks who might have a better chance than average of becoming superstars down the road. So there's actually incentive to be bad, which I think is not a good thing, and I think that the league should fix it. I don't know whether relegation is the answer to that. I don't know how drafting works or in systems with relegation. Like in American sports leagues, it's only the major league teams that get to participate in the major league draft, and that would be once again a truly major billion-dollar shift in focus if that were different. So I don't know whether it'd be better or not, honestly, but I do know that it's not going to happen in my lifetime. Rob Gebelis says, could the recent experimental results for non-constant dark energy alternatively be explained by modifying the properties of the dark matter sector, or even other assumptions of lambda CDM, or does it quite clearly point toward dark energy? Lots of things are possible. Certainly, it's full employment for theoretical cosmologists, right? So they are absolutely working on models where dark matter changes its mass over time. I was actually an author on one of the first papers proposing that dark matter could have time-dependent masses. Greg Anderson and I wrote a paper on what we called variable mass particles, or VAMPs. I thought it was a wonderful acronym. Did not catch on, sadly. I think that we were not the first paper. There was a previous paper by Juan Garcia Bellido that also had time-dependent dark matter. But this is back like in the 90s when people were not thinking about these things. So there weren't a lot of papers about it. And now there's many. You run into problems with models like that. The thing about cosmology is we now have a lot of observations. So you can't just say, well, I'm going to have dark matter change its mass over time. You have to say, okay, what does that do with structure formation? What does it do with the microwave background? What is the mechanism that lets the mass change? Does it lead to new forces? Does it need to lead to new dynamics and clusters and things like that? Gravitational lensing? There's a whole bunch of things that you have to do. And because lambda CDM fits all of the usual things pretty well, quite well, I would say overall, I think that the assumption is, except for the people who are literally making that particular model, that any one model is not all that promising. That could be wrong. If someone hits on the right model, then it might work. And so certainly people are incentivized to try, but I'm not like super optimistic a priori that that's going to turn out to be the right way to go. Armin Delenian says, you often argue compellingly that the quantum state in Hilbert space is your preferred ontology. In general, physicists select specific mathematical structures like Hilbert space or space-time manifolds to describe the world. What, in your current view, elevates any specific structure described in math to be real, distinguishing them from other abstract possibilities suggested by mathematical realism? How can one justify in believing in just one without believing in all? So I guess I could have grouped this with the previous question. I don't believe in a mathematical structure at all. I believe in the universe. I think that I want to understand the universe, and one way to understand the universe is to model it mathematically. So I don't think that there is Hilbert space and there is a vector in it. I think that there is the universe, and we can describe the universe, both its current state and its evolution, by mapping it onto a vector in this abstract mathematical Hilbert space. I'm not a mathematical realist. I don't think that any vector space is real. I just think that the universe is real. So the justification for treating this particular kind of mathematical structure as representing reality is that the theory fits the data. That's the usual justification for believing in one theory rather than others. Gordell says, you've discussed effective field theories, emphasizing the concept of an ultraviolet UV cutoff and how it prevents the details of very high energy physics from significantly affecting the physics at lower experimentally accessible energies. In other words, physics above the UV cutoff doesn't causally influence phenomena at larger, lower energy scales. In cosmology, we similarly talk about horizons, boundaries beyond which regions of the universe cannot influence or interact with us. Although we believe there is stuff beyond our observable horizon, it doesn't affect our local physics. Is the notion of a UV cutoff analogous to, or even mathematically equivalent to, a cosmological horizon? And if so, could that horizon itself possess some structure, such as geometry or other physical properties? No, is the short answer to this one. I kind of get the analogy that you're reaching for, but it doesn't really work for a few reasons. One is the cosmological horizon. I mean, there's one very big reason. There's sort of one reason that sounds good but is wrong, namely that is not really on point, I should say, namely that the cosmological horizon is something that happens at large scales and the ultraviolet cutoff is something that happens at small scales. So you wouldn't expect them to really be analogous in any simple way. And indeed, they're not. So it's not really true that in the spirit of effective field theories, high energy things have no effect on low energy things. That's not really the point. They do have an effect. The point is just that the effect that they have can be summarized in an effective field theory. That is to say, we can pick certain parameters for the low energy infrared field theory, the field theory that describes low mass, low energy particles, and the effects that high energy particles have on those low energy particles can be subsumed into shifting the parameters of the low energy theory, the coupling constants, the masses, and so forth. So the effects are absolutely there. They're just easily summarized in a small number of parameters. Whereas with the cosmological horizon, the effects are simply not there. That's the thing about horizons. You can't actually cross from one side of the horizon to the other, from the interior to the exterior anyway. So if there's something beyond our cosmological horizon, it literally has no effect on what goes on inside. That's a crucial difference between the two cases. Paul Torek says, Tim Maudlin has said on Robinson's podcast that the cosmological constant can be placed on either side of Einstein's field equations, and suggested that only putting it with the stress-energy tensor leads to thinking of it as dark energy. He seemed to imply thinking of it as dark energy is a bad idea. Is it a bad idea? Is it at least needlessly confusing? No, it is a very good idea. It doesn't matter what side of an equation I put things on, okay? The relevant physical fact is that vacuum energy contributes to the dynamics of the universe in exactly the same way as a purported fundamental cosmological constant would. The only physically relevant thing is the sum of those two things. You're welcome to imagine there is a fundamental change in Einstein's equation that appears on the left-hand side, and you call it the cosmological constant. But there is also something that appears on the right-hand side that you call the vacuum energy, and they have exactly the same form. So it is only the sum of those things that matters, and whatever question you have about the vacuum energy, that's the thing you have a question about. Samuel Benjamin says, have you ever prepared and delivered a best man speech? How did it go? Do you have any tips or tricks? I did once, actually. In fact, I originally thought when I read the question the answer was no, I hadn't. But then I realized I did, but it was sort of a gender-swapped thing where the bride's speech was given by a man, me, and the groom's speech was given by a woman. So I wasn't really called the best man just for tradition's sake. But I did give the little speech. And I've certainly been at other weddings and so forth. It's funny. At the one that I did give, the bride, who was a good friend of mine, it was an academic, a professor, came up to me afterward and was like, this is very interesting, like in a very academic professorial way. Like, I see the outlines of the genre, that you're always supposed to start with some gentle, good-natured teasing or making fun of the subject, but then at the end you switch to a sort of sincere, loving statement of what a wonderful and important person they are. And I think that makes sense, right? That's the thing. You should have fun in a good best man speech or bridesmaid speech. I don't know what they're called. You should, have some laughs out of the audience. You should keep it short because every speech should be kept short. You're allowed to bring up some, foibles of the person in question, but not in any mean-spirited way. I mean, be absolutely clear that you're not actually embarrassing anyone. You're not actually saying anything that would make someone upset or anything like that. That's not the point. That's not why you're there. That's not going to get you laughs. That's just going to get people mad at you. So you're allowed to poke gentle fun, but it has to be very, very gentle. And at the end, you should sum up with something that is absolutely sincere and straightforward and from the heart. David Sotolongo says, I'm curious what you think the odds are of democracy failing in the United States and Donald Trump becoming a dictator. It's hard to say something as simple as what are the odds. Certainly, the very relevant thing to say is that democracy is very much in peril now compared to what it used to be. Literally a couple days ago, as I'm recording this, there was an article that came out with a headline something like, political scientists say, hundreds of political scientists say U.S. is swiftly heading toward authoritarianism. That's not a headline that you got in the mainstream media that long ago. As I said before about expertise, if you're not an expert in something, the default should be to put a lot of credence on the opinions of many, many experts all at once. Many, many people who are experts in political science and history and things like that are more worried than the average person at the state of democracy in the United States right now. I think one important thing is that it's not an on and off switch. It's not like, oh, now we're not an autocracy, and then at some moment we will become an autocracy. You know, democracy will die on a certain evening. That's just not how it works. It's much more gradual than that. We've had, people abducted without due process. That is one thing that happens under an autocracy. We have had laws and regulations ignored. We have had court orders ignored. We've had steps taken toward making it harder to vote. We've had a bunch of steps taken making it easier to misinform and manipulate the public. We've had incredibly corrupt things where, just in the last couple of days, Donald Trump has been offering to have dinner with people who will buy his cryptocurrency. It's like blatant corruption. You're literally buying access to the president of the United States by spending millions of dollars that will go into his pocket. It's something that if any other president of the United States in history had done it, would be a major scandal on the front pages of newspapers. And with Donald Trump, you don't even hear about it because it's not even the worst thing he's done that day, right? So there's many, many aspects of the decline of democratic norms and safeguards and standards, and that's going to be the way it goes. And, people are saying, well, if Democrats win the House of Representatives, they should impeach Donald Trump. But as other people point out, what is the point? What is the point of impeaching? They're not going to win the Senate. The numbers are against them. And the Senate's just not going to convict him, no matter how bad the offenses may be, because it's all politics. It's not about reality at the moment. So in some sense, the democracy is a sliding scale, and we've already slid a huge amount. So there's a very on-off question. Is there a chance that Donald Trump could continue to be president for what would be a third term? And there were articles written less than a year ago saying come on, don't think that. That's just hysteria. You're being alarmist. But now Donald Trump himself is saying, yeah, we're looking into that. We're trying to figure out ways to make that happen. We don't know what exactly it's going to be. He wants to do it, certainly, because he will be thrown in jail if he's not actually the president anymore, because he's violated so many laws. So that'll be a test. That will be something that will be cut and dried. If Donald Trump is still the president 4 years from now, then effectively we no longer have a democracy in the United States. I don't know what the chances of that happening are. I still think they're less than 50%, the chances of democracy ending, let's say, in the next 4 years, effectively ending. But it's double-digit percentages, whereas before it was less than 10 to the minus 3 or 10 to the minus 4 under an ordinary presidency. So I think it's like I said before, it's an all-hands-on-deck, really bad situation, and it's not just me. It's not just a couple of alarmists on social media. It's the world's experts in this subject who are saying this, because they have a broader view than the typical person does. The typical American citizen has never lived under a dictatorship. They just think that it's not really something they need to worry about. It's not in their sphere of worries. Whereas if you study history or international relations or the notion of democracy worldwide, et cetera, you know that democracies end. You know the signs that it's happening, and you see the signs very, very vividly in this country right now. It's not about alarmism. It's very real. And I think we should act as if it's not like the risk of superintelligent AI. This is a high probability thing that would be completely disastrous, and we should act accordingly. Wade Dunn says, when you talk about cosmic inflation just after the Big Bang, it seems to violate the speed limit of the universe, the speed of light. What gives? Not when I talk about cosmic inflation. As we were talking about before with the scale factor of the universe, the scale factor is not a distance, right? The scale factor of the universe is a relative distance. If I have a galaxy and I can talk about the distance in some reference frame between us and a distant galaxy. And the galaxy is moving away, okay? but it's moving away, and there is some effective apparent velocity that we can define. At any moment, we have a Hubble constant, which is a number, and we have the distance, and the formula from Hubble is that the apparent velocity is the Hubble constant times the distance, the apparent velocity to a galaxy. So whatever the universe is doing, there will be a distance so big that the Hubble constant times that distance is an apparent velocity greater than the speed of light. What is going on with that? It doesn't mean things are moving faster than the speed of light. The rule in general relativity is that two objects cannot pass by each other at a relative velocity faster than the speed of light, and us and a distant galaxy are not passing by each other. There is no uniquely well-defined velocity between two objects at different points in space-time. You can only define velocity if the objects are literally next to each other. You can define quantities that have the units of velocity and act like a velocity, and that's what we do in cosmology. So there's nothing different than what happens now versus what happens during inflation. Inflation is a case where, as we were talking about before, the second derivative of the scale factor is a positive number, but the Hubble constant is still decreasing with time. There's the statement that the universe is increasing faster than the speed of light, which is a statement that people sometimes make, is simply nonsense, is literally grammatically incorrect, because the expansion rate of the universe is not a velocity. It does not have the units of velocity. It can't be greater than the speed of light. So if anyone says, and very, very smart people often say, inflation is a kind of superluminal expansion, they don't mean that. They probably know better. Don't listen to what they're saying, and certainly don't worry about violating the speed of light limit. Demo says, do black holes at the centers of galaxies have an effect on the structure, size of the galaxy, or are they just kind of there? That's a good question. I mean, in some sense, we don't know, because we don't know a lot about the formation history of these black holes. That's one of the big mysteries in cosmology, how these supermassive black holes came to be. In another sense, we know perfectly well these black holes are very tiny compared to the galaxy. The black hole in our Milky Way is, a few million times the mass of the sun. That sounds very big, but the galaxy is more than 100 billion times the mass of the sun. And that's a typical ratio for these kinds of situations. So there's no sense in which the black hole at the center of our galaxy is hefty compared to the galaxy. The overwhelming majority of mass in the galaxy is in the form of stars and dark matter and gas and dust and things like that. So in that sense, they're just kind of there. But there might have been feedback at early times when the black holes formed that had some relationship between how the galaxy formed and the black hole formed. That's what we don't really know about. Albin says, I've been seeing a ton of conspiracy theories online about the recent Blue Origin flight with Katy Perry. Stuff like it was fake, the door opening was staged, and mocking that the trip was too short. It seems like a lot of people just don't understand how space flight actually works. Wouldn't moments like this be a great chance for the science community to step in and explain things? It feels like a golden opportunity to turn all that viral misinformation into a teaching moment. I think it depends on what your goals are for that teaching moment. I'm sure that anything that is popular and involves science in some way could be used as a teaching moment, sure. But don't think that when you have a popular conspiracy theory, you can step in with the facts and get rid of it. Conspiracy theories are remarkably resistant to facts. And the way that you change people's minds about things is not just to give them better facts, because they didn't get to where they are by believing bad facts. They got there by a much more complicated process. What you should be asking is, why are people so susceptible to believing these conspiracy theories? Why are there's so many YouTube videos promoting these conspiracy theories? What is the need, the human desire that is served by believing these conspiracy theories? Because it's clearly very strong. I think that it's a much more comprehensive program that is needed to stop people believing these conspiracy theories so easily than simply going out there and laying some science on them. Charles E. Grant says, in playing with chatbots like ChatGPT and Claude, I've noticed that the bots tend to be very flattering, frequently praising the profundity of my insights or the penetration of my reasoning. I asked the bots if this was done to optimize engagement, which at some point would be monetized, even if the agreeableness made the service less genuinely useful. The bots agreed that this was highly likely. Now we're hearing that elements of the U.S. government want to use LLMs to replace large swaths of the bureaucracy. I worry that the public doesn't appreciate how malleable language models are. Whatever controls the training data and the objective function controls most of the final output. Do you think people are too worried about AI taking over the world for their own silicon purposes, when they should be far more worried about their fellow humans using credulity in AI as a means of political control and disinformation? I think I want to say yes to that last question. I'm not that worried about AI taking over the world. I think that's a mistake in attributing motivations and agency to AI that aren't really there. I am very worried about problems AI can cause, and political control and disinformation are among those problems. There are other problems. I was just talking the other day to someone who's married to someone who works in AI, and they let the AIs talk to each other, right, and then do things. And of course, all these AIs have access to the internet, so when they talk to each other, they can sort of suggest to each other, oh, you should start a Twitter account and start posting, and they go, yeah, I'll go do that. And this is not a matter of like motivation or anything like that. It's just that the human being has sort of pointed the gun and then let it fire itself. And it's that lack of control that I think can plausibly lead to terrible things. There's another thing that comes to mind. I'm not sure how exact the analogy is, but a friend of mine actually knows Mark Hemingkowski. You know him, recent Mindscape guest. Mark used to be a professor at Columbia University in New York City, and he told me the story of when the physics department had a visit from the head of security at Columbia, just not because there was an incident, just like, let's catch up on security practices and things like this. This is years ago, long before the recent brouhahas. And someone at the meeting, one of the faculty said, like, there's this door that is locked at a really useful time. It would be much more convenient if that door were unlocked. And the security chief said something that stuck with Mark, namely this. There is always an inverse relationship between convenience and security. You can only increase convenience by decreasing security, and when you increase security, you will decrease your convenience. I think this is as true for AI as it is for doors on your campus in an urban environment. We can choose to be safe with our use of AIs, or we can choose to be convenient with our use of it. Guess what? We're choosing to be convenient. I mean, the journey of OpenAI from a nonprofit organization devoted to AI safety to a very much for-profit organization that is working its hardest to be not safe in its use of AI, to put it bluntly, is just a case in point. There's so much money going around that AI is just not going to be used safely. And so those are the kinds of things. Yes, political control and disinformation, part of it, but also just like turning over valuable control of things to AIs because it's easy, because it's convenient and simple, and we'll worry about the safety features later. That's something I'm very, very worried about. Domino says, great episode with Annika Harris. I too am a physicalist and an Everettian, so panpsychism is a tough pill to swallow. I know Annika doesn't love that word, but her story reveals a shared paradigm between it and many worlds. What I find most intriguing about our interpretation of quantum mechanics, that is to say, many worlds, is the lack of hand-waviness. No hidden variables, no godly observers, just the Schrödinger equation. However, I have to say that the tenets of consciousness all the way down strikes a similar chord. No dualism, no arbitrary brain complexity justifications, just experience. Does framing her ideas in this way make them any more palatable to you? If branching universes is the cost of many worlds, is fundamental consciousness the cost of explaining the hard problem? On that standard, how many things do you have? Sure, Philip Goff has made this point. He says there are two things, consciousness and the physical material world, and I can explain both of them by saying there's just consciousness, and the physical world is something that emerges from that. It's just as simple as saying the consciousness emerges from the physical world. Sure, if that's the only criterion you have for the success of a theory, then that would be it. But there are other criteria like fitting the data and explaining the patterns that we see in the world. As I mentioned before, I don't see how a consciousness first approach explains all of what we know about matter and physical behavior. I can see, even though there's obviously research questions yet to be answered, how purely physicalist approaches will explain everything there is to be explained about consciousness. So in my mind, it is not a fair fight. Anonymous says, what are your thoughts on the recent announcements about biosignatures on K218b? This is a reference to a claim that came out it was a press release anyway, let's put it that way, about a team from, I think, Cambridge University who claimed to see certain molecules in the spectrum of a certain exoplanet and claiming those molecules are signatures, perhaps, of life existing on that planet. But almost right away, this announcement was attacked by the community of people who should know about it. I am not in that community. I am not a person who is an expert on this, but there's two claims. Number one, did they really see those molecules? And number two, are those molecules really signs of life? Both of which were very heavily criticized. And also the people making the claims were pretty harshly criticized on the basis of not being very careful about it, of trying to hype their own results more than those results really deserved being hyped. I think that generally whenever you get, this is something that Sarah Walker, a previous Mindscape guest, would say, whenever you have a very small molecule that here on Earth is often created by organic processes, but if it's small, you should be able to imagine non-biological processes that make it also. The real test case for biological assembly of molecules will be complicated, long, very specific molecules that are made in great abundance by something. That's something that life can do much better than non-life, and that's not something that we're seeing evidence for here, so I'm not getting very excited about this one. David Wright says, I was fascinated by how both sides of the political spectrum perceived the recent Signalgate intelligence leak. If you accidentally received a highly classified phone message from the head of a large foreign country that laid out detailed plans for a full-spectrum war, including economic, political, psychological, and military plans, what would you do? Would you present it to the public, protect your finances, keep it to yourself to avoid embarrassment? How would you handle this occurrence as a public figure with significant credibility and contacts? I'll just note that you changed the scenario a little bit because you said received a highly classified phone message from the head of a large foreign country. In the case of Signalgate, this is when Jeffrey Goldberg of The Atlantic, an editor, got mistakenly added to a text chain on was it Signal or WhatsApp? I don't even remember. I think it was Signal. Yeah, a purportedly secure but private web app that you can use to send messages on, and they were planning secret military operations on this app. And you're not supposed to do that. It violates a whole bunch of laws. Why would you do this? There's two possible explanations. One is that you are very stupid and you don't understand what it means to do things that are supposed to be classified. The other, which actually in this case I think is more likely, is that they know exactly what they were doing. And there are rules about, Freedom of Information Act and things like that, government records acts that preserve official government communications so that people can look at them later. And they don't want their communications to be preserved because they're doing stupid things. And that is why they don't use the official channels. So either way, it's bad. Like either one of the explanations is not at all good. Anyway, in that case, of course, Jeffrey Goldberg is an American citizen and he got communications from the American government, not from a foreign government. Okay, so it's a slightly different scenario. I think that Goldberg did exactly the right thing. I felt that he was very, very on point. At first he thought it was probably just a joke or spam or something like that, so he just didn't respond because you don't want to let the spammers know that you're even there. And then when it became obvious that it was real because he was seeing news stories that were only possible if this text chain were completely correct. Then he removed himself and informed the people that he was on there. And then he wrote a story about it because he's a reporter, which is perfectly okay. He didn't violate any laws. And in the story, he left out a lot of details because maybe they were classified, right? And then stupidly, the people who were involved, the government officials who were involved, claimed that there were no such details in the text chain. So, of course, then The Atlantic published the details because they wanted to prove that they were not lying. So I thought that they were perfectly fair. Journalists have that right to report on things, that he didn't break any laws to gather the information or anything like that. There are questions about what you should do morally rather than legally or, as a good public citizen. He only revealed what was in the text chain after the events that were described there. So he didn't compromise the safety or security of anybody. So I thought that was perfectly fine. What would you do if it were a foreign country and they were threatening to, declare war or do disastrous things? I don't. It would depend a lot on the details. I could certainly imagine myself alerting our government that we were about to be attacked by a foreign country. I think that's fair, depending on details. Once again. I don't think, keeping it to yourself to avoid embarrassment. Why would I be embarrassed by that? I mean, someone else might be embarrassed by adding me to a text chain by mistake. But I don't see why I would be embarrassed. I might want to protect myself from crazy people who are partisans of one political party or the other. That would be perfectly plausible. But there would be ways to sort of take that information and convey it to the media in a safe way while keeping my own anonymity. But I think that the number of variables at play in a scenario like this is so large that it's hard to have a specific policy worked out that I could promise I would obey ahead of time. Janko Bartelink says, if consciousness is an emergent property of a complex system such as our brains, it is probably not a coincidence that our brains are within a certain size domain relative to the atoms and molecules they are made of. Do you think that there's an upper limit to the size domain of complex systems attaining consciousness? And if so, what is the approximate maximum scale? I don't think there's probably a sharp upper limit, so I can't give you a number. I think that there's a lot of compromises going on whenever you do biology in any way. So you have, as we sort of mentioned about the question about the evolution of intelligence before, there are trade-offs. A lot of brain power requires a lot of energy, and it also gives you a vulnerability in a fight. The enemy can shoot you in the head or whack you in the head. It's a very obvious target for your enemies out there in the wild, in nature red in tooth and claw. So, but on the other hand, being intelligent provides you lots of advantages in planning and the ability to maximize resource use and things like that. As your brain gets bigger, then it gets even more resource intensive, I would imagine, in terms of the energy and the calorie intake that it would take to keep it going, even more vulnerable in some sense. So that's a constraint, but maybe you could become smarter. Maybe you don't become that much smarter. I don't know. Maybe it depends on a lot of details. It takes longer for signals to get from one side of your brain to the other. If the brain is smaller, then there's probably less processing power on all else being equal, so you're not as smart, So I don't know. I don't think that there's like a hard and fast cutoff, and it would depend on the gravity on your planet, if you were on another planet, and things like that. So again, many things go into it. I don't think you can I would not be surprised if let's imagine, conditionalize on the idea that we detect and get to explore 1,000 different intelligent species. I don't think that's very likely, but imagine that we did. I would not be surprised if most other brains were within a factor of 10 the size of ours, either a tenth smaller, certainly let's say within a factor of 100 the size of ours. I don't know whether it's overall better to be bigger or overall better to be smaller. We're fairly young, we're fairly recent in the game of being intelligent, biologically speaking, so maybe we haven't found that perfect medium quite yet. Peter Newell says, I recently watched your debate with Philip Goff for the first time, and I was wondering if your view on Mary's room has changed at all. I would summarize your position in the debate as, of course, Mary learned something new. Her neurons had never fired that way before, which makes perfect sense to me. However, Goff and some of the audience members seemed adamant that this completely misses the point of the thought experiment, and further, other physicalists, such as Daniel Dennett, seem to find it crucial to argue that Mary does not learn anything new. Since both sides seem to agree that physicalism requires Mary not to learn anything, it feels uncomfortable to be in the minority here. Do you think you were actually missing something? I seem to be missing it too. Well, I think that was, maybe I didn't come across very clearly, or maybe I'm misremembering what I actually said. That is not how I would summarize my own position. I would summarize my own position. I think everyone knows this thought experiment. Mary, the color scientist who is raised in a black and white room, so she never sees red, but she knows every physical fact about red in the science textbooks. Okay, she understands red intellectually, but she's just never experienced it. The question is, if she walks outside and now sees the color red and experiences it, does she learn something new? And the argument is supposed to be, if she does learn something new, well, she already knew all the physical facts, therefore there must be facts that are not physical facts, and therefore physicalism is false. The originator of this argument, Frank Jackson, has repudiated it. He actually has gone back to being a physicalist, but it sticks around, the argument, because people like it for some reason. My strategy was to say, who cares whether Mary learns something new? That is a semantic issue about your definition of what it means to learn something new. If you really think this thought experiment is a challenge for physicalism, then forget about whether Mary learns something new. The question is, can physicalism explain what happens? In other words, is there something that happens in that thought experiment that is literally incompatible with the precepts of physicalism? And I made the point that no, of course not. Nobody thinks that. Mary's in the room and she's reading books, and that means that certain neurons in her brain fire. She walks outside, she sees the color red for the first time, different neurons in her brain fire. All of that is 100% compatible with physicalism. All that we're arguing about is what words to attach to the neurons firing. But you're not going to disprove physicalism by arguing about what words to attach to the neurons firing. So I don't remember hearing anyone else make that argument before. It might be new. I don't know. I'm sad that it is not the majority view, but so be it for many views that I have. David Stern says, in Quanta and Fields, the last sentence of chapter 7, Scale, says, it will never cease to be amazing how the complexity of our everyday world is constructed from just a few simple elementary ingredients. That reminded me of the last paragraph of Origin of the Species. I'm particularly thinking of, there is a grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one. So I was wondering if you were influenced by Darwin, or perhaps the idea of complexity arising from simple rules is a strain running through the history of science. I was not consciously influenced by Darwin. I was not thinking of echoing that. If I had, I would probably have put more work into speaking more poetically than I really did. But I think it is, just a common theme of complexity arising from simplicity. It's certainly a theme in physics and certainly also a theme in biology. One would like to have a unified understanding of those two, which one does not quite have yet, but that's the kind of thing that we're working on right now. So hopefully progress is continuing to be made. Corey Leander says, what are your thoughts on America's fiscal sustainability? Do you think it's possible to cut our deficit in half by reducing overspending, not benefits, in Medicaid and Medicare while increasing the payroll tax cap and overall tax enforcement? Allegedly, there is $600 to $800 billion in uncollected taxes every year under the current tax code. So let me say two things right at the start. Number one, this is a purely academic question because we are not increasing tax enforcement. We are destroying tax enforcement. So we are losing huge amounts of money in the federal budget right now as we speak here in late April 2025. And the second thing is there's no such thing as America's fiscal sustainability. There's a bad analogy that people inevitably make between deficit spending by the government and deficit spending by an individual or organization. Human beings or corporations can go into debt and go bankrupt. They can run out of money. And that would be bad. And that sounds bad, and it is bad. The government is different. The government cannot run out of money because the government prints the money. The government decides how much money there is. The government could instantly wipe out its budget deficit by printing more money. Now, it doesn't want to do that for very good reasons. You don't want to just go around printing money. That would cause huge amounts of inflation, and it would hurt the economy dramatically. So there is an issue here. There's absolutely an issue about how to correctly balance government income versus government spending versus the money supply and interest rates and things like that. There's a big complicated dance that we have to do to keep the economy running well. So these are good questions, but you shouldn't think of it in terms of America running out of money. That's just not the issue. In terms of what to do, in terms of the budget deficit and things like that, again, that would have been an interesting question to ask a year ago, back when we thought that we still had responsible people in charge, and you could actually think about how much money should we be spending, how much income should we have. Nowadays, we're just trying to stay alive, right? It's perfectly legitimate to worry about what movie should we go see tonight. That's a conversation you could have. But if you're in the middle of a hurricane and you're worried about not drowning, that is not a good conversation to have. Clearly, I think it's perfectly obvious we don't do enough to collect tax revenues. I think that the tax rate should be higher, especially in high tax brackets. I think there's lots of complexity in the tax code that lets wealthy people and corporations avoid their tax burdens, whereas other people don't. I think that in terms of wasteful spending in the government, I'm sure it's there. I honestly don't have the expertise to figure out exactly what it is. I think there's a good argument to be made that we're spending too much money on the defense industry, but I honestly don't know the details. So maybe I'm wrong about that. We're certainly not trying hard enough to collect taxes and enforce the tax laws. That's been shown over and over again by studies. If we put more money into the IRS collecting taxes, we would collect more money by a lot than whatever we put in. So, there's all complicated things that in a sensible time would be interesting to talk about, but we don't live in a sensible time right now. Julie Evanoff says, I adopted gravity warps time as a moniker of mine, and I wanted to understand if I got it right. I wrote a sort of poem about how gravity warps time. Could you read and correct any aspect that I have wrong? An exploding star transforms into gravitational waves that form a field. The field of waves moves through the universe with speed and direction. The field warps the space-time continuum as it travels. When the field passes over a small planet, the warp is measurable using light beams, tubes, and a clock. I think that's almost true. I would have a couple of footnotes here. The field, the gravitational field, is there before it starts waving. Gravitational waves do not form a field. They are a disturbance in the gravitational field. The field itself doesn't move through space. The disturbance moves through space. And it does have a speed. It has lots of directions. It's a wave. It's a wave moving all in many directions at once. So it doesn't have a single direction. The second two sentences are completely fine. The field warps space-time as it travels, and we detect it with light beams, tubes, at a clock. The other thing, which is very much a nerdy kind of footnote here, is that exploding stars are a bad example of the formation of gravitational waves. They do form gravitational waves, but relatively small amounts. There's a theorem in general relativity that says that if you have a distribution of matter that is perfectly spherically symmetric, it does not make any gravitational waves at all, even if it moves a lot. So if you had a star explode like a supernova, in the limit where it is perfectly spherically symmetric, you get no gravitational waves, even though you have a giant cataclysm of a star exploding. That's why the actual gravitational wave detections that we have are not from exploding stars. They are from binary black holes or black holes and neutron stars spiraling together and coalescing. In principle, real supernova explosions are not perfectly spherically symmetric, so there will be some gravitational waves, but it's not a primary source that we pay attention to or look for. Fabian Rosdalin says, I've heard many proponents of different consciousness as fundamental theories use the observer in quantum physics as a basis for their arguments. But to me, this seems like a fundamental misunderstanding of what is meant by observer in this case, and thus a very bad starting point for any argument. So far, I haven't heard any one of them even acknowledge this misunderstanding, not even in conversations with you. So do you think it is really just a misunderstanding, or is there something there that I'm missing? I think it's mostly a misunderstanding, but I see where the misunderstanding comes from. There is a problem in quantum mechanics. And if you just look at the way that it's taught to undergraduates, the word observe or measure appears in the rules of the theory in a way that it doesn't appear in the rules of any other theory in physics. And this is a puzzle. This is the measurement problem. Okay, this is a legitimate puzzle. And back in the early days, in the 20s and 30s, the existence of this idea of observing or measuring made people wonder what that meant. Did it really mean that you had to be a conscious observer to make quantum mechanical measurements and make the wave function collapse, et cetera? People like famously Eugene Wigner really tried to develop that into a scientific theory. These days we know better. These days we have very explicit mechanical examples of what it might mean for the wave function to collapse, whether it's decoherence in many worlds or some other mechanism. We have proof by construction that you don't need to talk about consciousness to talk about quantum measurements. But that is a fact about quantum mechanics that a lot of people who talk about consciousness don't know, that we don't need that discussion anymore, that the real experts in quantum mechanics don't talk that way anymore. I'm doing my best to help them know that, but I'm only one guy. Lee says, how do you feel about the Apple App Store policies dictating how you price your Patreon? Well, I don't like it, but I'm kind of helpless in the face of the giant multinational corporations that have a lot more power than I do. So for those of you who don't know, I still haven't done it because I've been busy and been doing other things, but we're going to have a new policy on the Patreon where you pay by the month rather than by the episode. It's not a big deal. I just got to do it. I just haven't had time to do it yet. I don't think it's the worst thing in the world. Paying $5 a month or $4 a month, I don't know how it will work. Isn't that different than paying $1 per episode, right? It's inflation. There's inflation going on all over. So paying 25 cents more per week is not a big deal. And might even be more convenient for some people. And I'll tell you, the original reason why the policy was per episode, why my personal policy was per episode, lots of people said, don't do that, do it per month. And I said, well, I'm not sure I'm going to put out a podcast every week, so I can't promise that people will have one podcast every week, so I don't want them to pay per month because I don't want to underserve them. But now, several years later, I've been putting out one podcast per week, so I think that paying by month is fine. I wish we had infinite flexibility to do it, but I use the services of these multinational corporations. Sometimes I have to bow down to their whimsical rules. Hussein says, in your last AMA, you rightly criticized the Trump administration for its fascist policies, mentioning the kidnapping of Fulbright scholar Rumeysa Öztürk for her op-ed opposing the United States' support for Israel's policy in Gaza. But I sensed some discomfort when you were framing her op-ed, and it struck me that over the past 16 months, you've largely avoided discussing Israel's assault on Gaza, despite the topic's enormous role on college campuses in the past year. I don't think that discomfort is accidental. Frankly, we've seen students, faculty, and officials targeted not just for being pro-Palestinian, but specifically for failing to be sufficiently pro-Israel. So my question is, are you personally concerned about retaliation for speaking out on this issue? And if not, is there a reason you've seemingly given it less attention compared to other similarly relevant topics? It's not at all concerned about retaliation. That is not what is going on. And in fact, it's not even discomfort. If you detected anything, it was me trying to be careful talking about something that I'm not an expert in. I glanced at the op-ed that Rumeysa Öztürk had written, but as someone who's spent a lot of time on college campuses, I'm very well aware of the syndrome where people who don't know what is going on a certain college campus dip in and read some op-ed in a student newspaper and then make grand pronouncements on the basis of it when they have no clue what the wider context is. And I don't want to be one of those people. For Israel versus Palestine in general, I just am not interested in talking about it. It's one of those situations where there's no lack of talking about it. The world doesn't need me talking about it. It's not like anyone hasn't heard of it because I haven't been here talking about it on Mindscape. I have nothing to add to it. I have no special knowledge of what is going on, and it's not interesting or fun to talk about because the people who do talk about it have chosen sides. They have figured out which tribe they are in, and they go along with that tribe, and they talk in a way that is not especially thoughtful or rational, to be frank. I think there are tragedies going on. I think that the attack on Israel on October 17th was a tragedy. I think that Israel's retaliation and bombing of Gaza and the killing of many innocent people is also a tragedy. There's lots of tragedies going on. What can I do about this? I really don't know. So the world doesn't need me talking about it. I would not add any light to the heat that is already in great supply. The Memes of Destruction says, I've heard that dark energy can be thought of as the curvature of space. Is there any truth to this or intuitive way to conceptualize it? Nope, there is no truth to that. It's energy. The dark energy is energy. That's why it's there in the title. It's energy just like the mass of the Earth is energy, E equals mc squared, or the energy in the radiation in the cosmic microwave background is also energy. Energy causes space-time to curve. The curvature of space-time is measured by the metric tensor, or if you want, it's characterized by the Riemann curvature tensor that you construct from the metric tensor. Dark energy is a source of that curvature. It is not itself curvature. Murray Dunn says, what is known about the presence of dark matter in our solar system? Well, what is known on the basis of actually experimenting is very, very little, almost nothing. What we can do is create a model of dark matter in the universe and then ask what that implies about dark matter in the solar system. So there should be dark matter in the solar system, a higher average density than in the universe because the solar system is in a galaxy. But the thing you got to keep remembering about dark matter is it's not sticky. Ordinary matter is sticky. We think that there's a good reason why, in fact, you can test observationally, experimentally, dark matter is spread out more than ordinary matter is. We talk about a dark matter halo, and a visible galaxy is a small thing living at the center of the halo. And the reason why is because the visible matter is made out of sticky atoms, and they bump into each other, and they stick there in the middle, whereas dark matter just goes right through the middle and out the other side. And so it does collect into what we call a halo, but that halo is much more diffuse and lower density. So there's not especially more dark matter here in the solar system than there is elsewhere in the galaxy, not in the solar system. But we think there should be some. There could be local variations, right, in the density because of the dynamics over billions of years. That's an interesting topic that people think about. And so that's a little bit of a source of uncertainty for experiments that are trying to directly detect the dark matter here in the solar system. Bits plus Atoms says, what is the last time you said WTF or thought it to yourself? What was the situation? WTF meaning what the fuck, I presume. It's late in the podcast, so we can use the bad language. I'm not even going to mark this podcast as using bad language. I'm just going to run that risk. We're just going to be rule breakers that way. I remember very explicitly when the last time I used that, at least I remember the last time I remember using it. How about that? Which was, it's not a phrase I often use, but we were just moments ago talking about the abduction of Rumeysa Öztürk, and I was so shocked by the video of that I put it on Blue Sky, and my entire commentary was, what the actual fuck? I can't believe that our government is doing this. A bunch of plainclothes people in masks without any identification are picking up a college student off the streets and loading them into a van and taking them off and not telling anyone what is going on. I can't believe that's my country anymore. That's the last time I remember saying that. Marie Roskew says, I've recently read an article about people voting for right-wing populists or people with extreme views. The journalist says that people voting for politicians with extreme values and views are those who feel excluded from society, e.g. people who can't afford education or healthcare, etc. These excluded people are intentionally choosing leaders who will subsequently destroy the current society. Where do you come down on such an option or idea? I think that sounds overly simplistic to me. I don't know who wrote the article. This is, again, the kind of situation where it is very easy to come up with opinions. It is very hard to test these opinions scientifically. And so I'd rather talk to an expert political scientist about this. I do feel that there are lots of people in our society who feel excluded or alienated or powerless. I think there's overwhelming evidence for that. I think that it is a failure of our society that so many such people exist. I can imagine causes for that failure, but I'm much less confident in my diagnosis of what the causes are. It doesn't sound right to me to say that people are intentionally choosing leaders who will destroy the current society. I think very few people want that. They want dramatic change, but they wouldn't put it themselves in terms of destroying the current society. So I feel my first impulse would be to take them at their word. It might be that the way they go about causing dramatic change ends up destroying the society, but I generally don't think that's what they want. I mean, there's lots of evidence that people don't take politics that seriously, that they kind of treat it as entertainment, and they think that it'd be kind of fun to shake things up. And I think that's an aspect of, the question we've been getting a couple times over the course of this AMA: how do we make people better citizens? Like I know very highly educated, smart people on both sides of the political spectrum who fundamentally just don't take politics seriously. They think like, I'm not interested. Like, all the parties are the same. It doesn't matter what I do, blah, blah, blah. And the existence of many, many such people absolutely leads to the kind of decadent, not very responsive politics that we have. It is their fault in a very real sense that we're in the mess that we're in right now. So I want people, among other things, to not just be better informed or better Bayesians. I want them to care about politics more. I want them to think that what they do politically, even if it's just going to the voting booth once every 4 years, matters. And it matters not just for expressing their feelings, it matters for running the country and what will eventually happen. So I want people to feel responsible for what happens and to try to do their best. We should all try to do our best in that realm as well as others. I'm going to group two questions together, one from Carroll Cantor, who says, can you describe some experimental results or observations, even if currently far-fetched, that would definitively settle the debate on the interpretation of quantum mechanics? And Eric says, can you speculate on how advances in quantum foundations might practically impact regular physics like quantum gravity or cosmology? The shut up and calculate school takes it for granted that whatever interpretation you have of QM can have no impact on regular physics, but maybe they are wrong. So both of these are about possible experimental or technological impacts of different interpretations of quantum mechanics. So, as I've sometimes said, the phrase interpretation of quantum mechanics is outdated. That is something that we argued about in the 1930s, okay? But nowadays we have different theories of quantum mechanics. If you have an objective collapse model or a pilot wave model or an Everettian model, these are literally different physical theories. In some cases, there are very obvious experimental tests you can do. The objective collapse models are very experimentally accessible. You could detect a collapse. If you detect an objective collapse of the wave function in a very controlled environment, you will have falsified the alternatives to that model. You would have falsified Bohmian mechanics and Everettian quantum mechanics. There you go. Very, very falsifiable. If you don't detect the objective collapses, I think that the objective collapse models are also falsifiable. I think because, you might say, well, maybe the collapses become more and more rare or something like that, but you need them to be of a certain frequency to make the whole plane get off the ground. So I think that in principle, you could sort of rule out all of the parameter space. That doesn't mean you can test every theory, that you can test Bohmian mechanics versus Everett, for example. I think that you probably can, but I don't think that it's well understood. There are absolutely claims that you can't. There are claims that Bohmian mechanics will always give you the same answer as Everett, but I don't know if that's actually true or not. As to whether or not advances in quantum foundation might practically impact regular physics, it's not, it's never, I'm going to say this again in a second for another question, but it's never, the way that science goes forward is just not in this simple-minded picture you have where we propose a theory and then we test it and then we propose a better theory and test it and blah, 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 blah. It's this constant give and take between all sorts of things. Better theoretical understanding of the ideas themselves, better experiments, better ideas of how different theories fit in together, better appreciation of what needs to be explained. A whole bunch of things happen. And so it's just not a very simple picture. It's absolutely clear to me that better understanding of quantum foundations can have a huge impact on quantum gravity or cosmology. I think it does have an impact on quantum gravity or cosmology because it suggests certain questions to ask. The questions that I myself am working on right now are ones that are suggested by thinking hard about the Everett interpretation of quantum mechanics. Now, the proof of the pudding is in the tasting. It will only be persuasive to others if we actually make progress on quantum gravity because of these things, but it's certainly clear to me that you could, in principle, be pushed in the direction of progress. Bob Zanelli says, critics of the cosmic inflation proposal argue that this proposal is not falsifiable because you can postulate many different potentials, and all inflation models seem to require fine-tuned initial conditions. However, the Planck data, constrained by the limits of the tensor-to-scalar ratio, based on BICEP and Keck, is strongly supportive of the Starobinsky inflation model and has ruled out all models with standard scalar field potentials. This seems like progress. Does all this influence your credence on the cosmic inflation proposal? Look, I always thought it was silly to say that inflation is not falsifiable for exactly the reasons I just talked about. This whole idea that there's this crisp, clean line between falsifiable theories and non-falsifiable theories was never right. It was never true. Philosophers know perfectly well it's not true. The philosophers have thought about this carefully. Scientists are less good at thinking through these things carefully, so they pretend that there is a clear, bright line there, but there's just not. You work at it. You try to develop the theory. You don't just falsify it. You think about it. You say, well, all right, if this theory is true, then this other thing might be true. Let's look to see if that's true. I like to use the example of cosmic strings. Cosmic strings were an idea. They are an idea. They might still be true. It's not very popular these days, but before we measured the fluctuations of the microwave background, cosmic strings were a competitor to inflation for being the source of density perturbations in the universe. They made a prediction. That prediction was falsified by the actual measurements of the CMB anisotropy. So inflation remained viable. Inflation could have been falsified if you had gotten different. Sorry, let me say that exactly correctly. The idea that inflation was the source of the primordial cosmic perturbations could have been falsified by the spectrum of the cosmic microwave background. If it had looked like the predictions from cosmic string models, we would have stopped believing that inflation was the origin of that. Likewise, we did stop believing that cosmic strings were the origin of those perturbations. But that doesn't mean that we would have falsified the idea of inflation, nor that we did falsify the idea of cosmic strings. You could still have cosmic strings in the universe, but maybe they're just too low scale, too low energy to be the source of the initial perturbations, right? They could still exist, but they just might not be doing that particular job. And indeed, there's a parameter in cosmic string models, basically the energy density of the cosmic strings. And there's more or less, the number of cosmic strings you expect to exist in simple models of the early universe doesn't depend on the energy density along the string. Therefore, as you tune that density to be lower and lower, the number of strings stays the same. So the total amount of energy in cosmic strings goes down and down as you make that parameter lower. So you could make it, in principle, whatever observation you do to look for cosmic strings can at best put an upper limit on the energy per unit length of the cosmic string, because as that number goes to zero, all of the observable effects go to zero. In that sense, the cosmic string theory is not falsifiable. There is a free parameter that lets you avoid any possible experimental constraints. But you could actually detect a cosmic string, right? You could actually, maybe the parameter is big enough that you could easily see the impact of a cosmic string. Now, it would be completely bizarre and inexplicable if we detected a cosmic string for some scientist to say, no, I don't believe it, because that theory is not falsifiable. Because if the parameter had been some other number, we wouldn't have been able to rule it out. That's just crazy, right? And the same thing for inflation. If we find that inflation fits all of the data, that we have some very specific model that fits all the data perfectly, and we get the tensor modes and whatever, who cares whether there's other parameters where it wouldn't have been falsifiable? That's just would be a very strange way of thinking. Andre Linde once said, the way to rule out inflation is to invent a better theory. And in some sense, that's right. You know, we're comparing different theories. We're not just looking at individual theories in their own right. We're saying, given everything we know about the universe, what is the best way of thinking about it that we have right now? I'm not saying that way is inflation, but if it's inflation, then I really don't care that in principle it's not falsifiable. Jeffrey Siegel says, the conversation with Christoph Koch and people in an unresponsive state made me curious about your views regarding do not resuscitate orders. For example, currently I have a DNR order in place. But if there is a device that can determine whether my brain is still capable of higher order thought, as discussed in the podcast, I wonder if I should modify the DNR order to depend on the measurement of the brain complexity. On the other hand, even with a high measure of brain complexity, how long would I want to be kept alive if I am behaviorally unresponsive and potentially not receiving any external input? That would be a terrible way to stay alive. What do you think? This is a super important question. I'm glad that you asked it, Jeffrey. I'm not going to give anybody any medical advice or any advice about what to put in their DNRs. And even if I did give that advice, you should not listen to me because I do not know lots of things about the relevant medical questions here. And those medical questions include, can we feasibly and reliably do measurements to ask whether people are still conscious even though they are completely unresponsive? What are the chances that a completely unresponsive person could become responsive in the future? What are the thoughts going through an unresponsive person's mind? Would they rather end their lives or would they rather stay in that unresponsive state? I have no idea about the answer to any of these questions. All I can say is I'm glad you're thinking about it. My rough impression is that this consciousness meter that Christoph wants to have is not something that is like an off-the-shelf technology that has been perfectly well tested. So I don't think that he means for it to be affecting anyone's choices about DNRs right now. You'd have to ask him about that. But I do think that, it's a deeply, fiercely personal decision how to think about that. Personally, if I knew that I was going to be unresponsive, even though I was conscious forever, then I would be happy not to be resuscitated under those circumstances. I'm not someone who thinks it is important to remain alive no matter what is happening. I think that there is a point past which it's time to go. Okay, I have entire respect for people who don't think that. I don't think that's an absolute moral thing. It's a very individualistic thing. So you got to figure that stuff out for yourself. Sander says, in one of your lectures on emergence, you described modeling the emergence of complex patterns in coffee with milk. You mentioned that random motion of different molecules was not enough, but that complex patterns only arise with correlated motions. What prompted you to test for correlated movement? I think, again, it has to do with the scientific practice that we've been talking about before. You have a back and forth. We did some numerical simulations. Actually, we wrote a version of the paper where we claimed complex structures did arise out of individual molecule motions, but we had made a mistake, so we realized our mistake. And then we realized that in none of the simulations we did with individualistic local motions were we seeing complexity develop. But we knew from our experience literally mixing cream with coffee, not to mention our experience looking at the universe and the evolution of structure in the universe, that it is possible for complexity to come into existence. So what were our models missing? And one thing that is true both in the universe with the existence of gravity and in cups of coffee with the existence of spoons is that there is some large-scale push that leads to correlated motions. And so we put that in and voila, some complexity became very apparent in the data. So, that's how it works. That's how you invent hypotheses. You look at the data, you don't fit it, you go, what do I need to do? And maybe you come up with a good idea. Robert Ruxandrescu says, how would the laws of physics have to be in order for the second law to be such that there's a higher probability for low entropy in the future? To me, it sounds like reversing time and keeping the laws of physics the same, but I'm wondering what details I am missing. No, I don't think it's that. Of course, you can imagine states, microstates of a physical system that are very, very delicately tuned to make entropy go down as the dynamical laws do their thing, even if the individual dynamical laws are perfectly time reversal invariant. But those same dynamical laws would lead to entropy going up if you had different initial conditions. So that's not a question about the laws of physics. That's just a question about your initial conditions. I think what you're asking is, could the laws of physics be changed so that low entropy in the future was sort of robust and inevitable under a wide variety of different initial conditions? That can't happen if the laws of physics are reversible in time, which they are, as far as we know. So you would have to invent irreversible laws of physics, and you can do that. I mean, think about billiard balls, or think about molecules in a box of gas, right? Think about molecules just bouncing around. We often model them as billiard balls, like perfect elastic collisions, like little hard spheres. That is a way that you can sort of a toy model for statistical mechanics, and that's perfectly reversible. Elastic collisions are reversible. But imagine, not because of any subtleties in photons or molecular dynamics or anything, but just imagine I made up new laws of physics that said when two atoms bump into each other, they stick. They violate conservation of energy, okay? So they just stick to each other. They don't emit photons, so it's not like a normal inelastic collision in ordinary physics where the extra energy goes into either, changing the shape of the molecules or releasing. In ordinary physics, energy is really conserved, but it's hard to keep track of it. I'm imagining physics where energy is not conserved, where when two molecules hit each other, they just stick together. Then generically, I can start with a high entropy state with all the molecules spread out, and I let them move around, and they bump into each other, and as they bump, they stick, and they make bigger and bigger sort of conglomerations of molecules. And you end up with a configuration that is lower entropy than you started with. But those dynamics are irreversible because once you have two molecules stuck together, you don't know what their previous state was. You cannot undo that just using the laws of physics. So that would be a very different world than the world, I think, in which we live. Andrew Goldstein says, I read your September 2024 publication, What Emergence Can Possibly Mean, prompting me to ask this question. Is there an example where strong emergence has been resolved to lower level properties as a result of new observations and understanding? In other words, non-reducible emergent properties turn out to be reducible to lower level properties. I don't know. That's a good question, but I don't know of an example where everyone thinks it is strong emergence. According to the rules in our paper, in order for strong emergence to happen, there has to be something that only manifests itself at the larger level, at the more macro, more emergent level, the higher level, that is invisible in your favorite theory of the dynamics of the lower level. And I strongly believe that if your lower level is quantum field theory and particle physics, that just doesn't happen. It's conceivable. I just don't think the physics works that way. If your lower level is something that is already complex, like people, or maybe even like molecules or cells or something like that, then I can imagine something like that happening. But that's exactly the situation in which we have less control over what happens, right? That we understand the situation less. So I don't know if there's any good, clean, crisp example of that kind of thing. It'd be very interesting to look for and to study. Okay, my voice is giving out. We made it a long ways here. We have the last question of this month's AMA is from Rory Cochran. Like many others on here, I would love to have a discussion with you one day. I wonder whether you would consider auctioning off a telephone call with you to raise money for the Mindscape scholarship. Or perhaps you could raffle it off so that you do not end up just having to speak to the person with the most money. Or perhaps that sounds like an absolute nightmare. No, look. Talking to people is not a nightmare. I'm happy to do it. I enjoy doing it. I just don't have time to do it. I don't even have time to set up a raffle to do it. And I hope that people contribute to the Mindscape Scholarship at bold.org anyway. Literally this AMA that I'm doing right now, and I do every month, is what I take to be the best compromise between the fact that I don't have time to do everything I want to do and the fact that it would be fun to talk to lots of different people about lots of different things. This is my way that I can quasi have a conversation. I know it's deeply unsatisfying because you don't get to have a give and take. AMAs are not about give and takes. And I know some people try to make them that way by asking follow-up questions over and over again. And I generally ignore them because that's not the spirit of the AMA. So it's not what everyone wants. I get that, but it's what I'm able to give, and I enjoy giving it, and I want to enjoy giving it. I don't want it to become a burden or anything like that. So no raffles are going to be set up. Sorry about that. If you want to donate $5 million to Johns Hopkins and support an endowed professorship in natural philosophy that we could give to somebody, then I promise to have dinner with you and have a conversation. How about that? That's my compromise. I think we can all agree on that. Who knows? Maybe it will work. You never know. Anyway, short of $5 million, I am extremely grateful to everyone who supports even $1 per episode for Mindscape here on Patreon and elsewhere. I'm grateful to everyone who listens one way or the other. Hope you had a good time this month. Talk to you next time. Bye-bye.